Have you ever wondered what creatures ruled the seas millions of years before whales and dolphins? Long before our modern marine mammals took to the water, there was a different kind of marine giant that dominated the world's oceans, the Plesiosaurs. These fascinating creatures have captured human imagination since their first discovery, but what exactly were they, and how did we come to know about them? Let's journey back to the early 1800s, when a remarkable discovery would change our understanding of prehistoric life forever. In 1811, along the rugged coastline of Lyme Regis, England, a young girl named Mary Anning made a discovery that would shake the foundations of science. She uncovered the first complete plesiosaur skeleton, a finding that would eventually help us understand that Earth's history was far more complex and ancient than anyone had previously imagined. But what exactly was this creature that Mary Anning found? The plesiosaur was unlike anything alive today. Imagine a creature with a long serpentine neck, a tiny head, a barrel-shaped body, and 4 powerful flippers that it used like underwater wings. These weren't dinosaurs, though many people mistakenly think so. They were marine reptiles, perfectly adapted to life in the ancient seas of the Mesozoic era, living alongside the dinosaurs but following their own evolutionary path. The name plesiosaur itself tells us something about these creatures. It comes from the Greek words plesios, meaning near, and sauros, meaning lizard. Scientists chose this name because these animals showed features that were somewhat similar to lizards, yet clearly different. They were near lizards, but not quite the same. What makes plesiosaurs particularly fascinating is their unique body plan. No other animal, living or extinct, has ever evolved their distinctive combination of features. Think about it. What other creature has ever had 4 large wing-like flippers, a neck that could be longer than its entire body, and a body design that remained relatively unchanged for over 135 million years? This is longer than the time that's passed since the extinction of the non-avian dinosaurs. The discovery of plesiosaur fossils raised intriguing questions that scientists still grapple with today. How did they use their long necks? What did they eat? How did they move through the water? These questions have driven research forward and led to remarkable insights into ancient marine life. We now know that plesiosaurs weren't just one type of animal. They were an entire order of marine reptiles with incredible diversity. Some, like Elasmosaurus, had necks containing more than 70 vertebrae. Compare that to humans, who have just 7 neck vertebrae. Others, like Chronosaurus, evolved shorter necks and massive heads, becoming apex predators of their time. The legacy of these ancient marine reptiles extends far beyond their fossils. Their discovery helped establish paleontology as a scientific discipline and contributed to our understanding of evolution and extinction. They showed us that life on Earth has taken many forms over time, some so different from modern animals that they challenge our imagination. But perhaps the most important aspect of the plesiosaur's legacy is how it continues to influence science today. When we study these ancient creatures, we're not just learning about the past. We're gaining insights into how life adapts to aquatic environments, how major ecological changes affect marine species, and how complex body plans evolve. The story of plesiosaurs also reminds us of the importance of fossil preservation and study. Every new plesiosaur fossil discovered adds to our understanding of these remarkable animals. From that first discovery by Mary Anning to the latest finds in places like Australia's outback or Morocco's desert, each specimen helps us piece together the story of life on Earth. As we continue to explore our oceans today, the legacy of plesiosaurs raises interesting questions about marine adaptation and evolution. What can these ancient swimmers teach us about the evolution of marine life? How do their adaptations compare to those of modern marine animals? And what might their extinction tell us about the challenges facing marine life today? The story of plesiosaurs is more than just a tale of ancient marine reptiles. It's a reminder of Earth's incredible history and the countless forms that life has taken over millions of years. It shows us that reality can be more fascinating than fiction, and that some of the most important scientific discoveries can come from the most unexpected places and people. So the next time you look out over the ocean, remember that long before our familiar whales and dolphins, different giants ruled these waters. The legacy of the plesiosaurs lives on in the fossils they left behind, in the scientific questions they continue to raise, and in our ever-growing understanding of life's amazing journey through time. Let's dive deep into one of the most fascinating chapters in Earth's history, the Cambrian Period. Have you ever wondered what our oceans looked like roughly 541 to 485 million years ago? This was a time of unprecedented change, when life on Earth underwent a transformation so dramatic that scientists call it the Cambrian explosion. Imagine an ocean teeming with creatures so strange that they would seem alien to our modern eyes. During the Cambrian period, something remarkable happened. Life suddenly burst forth in an incredible diversity of forms. But what exactly made this period so special? Before the Cambrian, most life was simple, soft-bodied, and small. Then, almost like a switch being flipped, the oceans filled with an amazing variety of complex animals. This is when we first see the appearance of most major animal body plans that exist today. Think of it as nature's greatest experiment in biological innovation. One of the most important developments during this time was the evolution of hard parts, shells, exoskeletons, and other protective structures. This was a game changer for life on Earth. These hard parts not only provided protection from predators, but also left behind excellent fossils, giving us a detailed window into this ancient world. The Burgess Shale in Canada has provided us with some of the best evidence of Cambrian life. This exceptional fossil site preserves not just hard parts, but also soft tissues, giving us an unprecedented look at these ancient animals. Here, we find creatures like Anomalocaris, a fearsome predator that grew up to a meter long, massive for its time. With its disc-like mouth and large frontal appendages, it was one of the first complex predators in Earth's oceans. Another fascinating creature was Hallucigenia, which puzzled scientists for years after its discovery. Initially reconstructed upside down and backward, this small animal walked on spiny legs and had a row of tentacles along its back. It's a perfect example of how bizarre and unfamiliar Cambrian life could be. Trilobites, perhaps the most iconic Cambrian animals, first appeared during this time. These arthropods, related to modern crustaceans and insects, became incredibly diverse, with over 20,000 species eventually evolving. They developed complex compound eyes, jointed limbs, and protective armor, innovations that would prove successful for hundreds of millions of years. The Cambrian also saw the emergence of the first vertebrates, our earliest ancestors. Small fish-like creatures called Picaina and Hyquicthes show the humble beginnings of the backbone that would eventually lead to all fish, amphibians, reptiles, birds, and mammals. But what triggered this explosion of life? Scientists have proposed several theories. One key factor was likely an increase in oxygen levels in the oceans and atmosphere. Complex animals need lots of oxygen to power their active lifestyles, and evidence suggests oxygen levels rose significantly just before the Cambrian. Another important factor was the development of predation. As some animals evolved to become predators, others had to develop defenses, shells, spines, armor, and the ability to burrow or swim quickly. This evolutionary arms race drove innovation and diversity. The development of complex sensory organs, especially eyes, also played a crucial role. When animals could better detect their environment and other organisms, it sparked new behaviors and interactions, leading to more evolutionary changes. The Cambrian period also saw important changes in ocean chemistry. The seas became rich in minerals that animals could use to build shells and skeletons. This availability of building materials enabled the evolution of many new body forms. What's particularly fascinating about the Cambrian explosion is its speed in geological terms. While taking place over several million years, this was still remarkably fast compared to other major evolutionary transitions. It's as if life had been waiting in the wings for millions of years, then suddenly rushed onto the stage in an incredible variety of forms. The legacy of the Cambrian period continues today. Many of the basic body plans that evolved then are still seen in modern animals. The bilateral symmetry, segmented bodies, and specialized appendages that first appeared in the Cambrian are still fundamental features of animal life. Understanding the Cambrian explosion helps us appreciate how life on Earth can undergo dramatic changes when conditions are right. It shows us that evolution can proceed at different speeds, and that innovations in one area, like predation or sensation, can trigger cascading changes throughout the ecosystem. As we face modern environmental changes, the lessons of the Cambrian period become increasingly relevant. How will life respond to our changing world? What new innovations might evolve? The Cambrian explosion shows us that life has a remarkable ability to adapt and diversify when faced with new challenges and opportunities. Have you ever wondered what it would be like to meet the most successful animals that dominated Earth's oceans for over 270 million years? Let me introduce you to Trilobites, the extraordinary arthropods that ruled the ancient seas and left an indelible mark on our planet's history. Trilobites first appeared during the early Cambrian period, approximately 521 million years ago, and persisted until their extinction during the Permian-Triassic extinction event, about 252 million years ago. But what made these creatures so remarkable, and why did they manage to survive for such an incredibly long time? The name Trilobite comes from their distinctive three-lobed body structure. A central axial lobe flanked by two pleural lobes. Their body was divided into three main sections: the cephalon, head, the thorax, body segments, and the pygidium, tail. This efficient body plan proved to be incredibly successful, allowing trilobites to adapt to various marine environments and lifestyles. One of the most fascinating aspects of trilobites was their sophisticated compound eyes, among the earliest known complex visual systems in the animal kingdom. These eyes were made up of calcite crystals, forming arrays of tiny lenses that provided them with excellent vision. Some species had eyes mounted on stalks, while others had eyes that covered nearly their entire head, giving them almost 360-degree vision. This advanced visual system gave them a significant advantage in hunting prey and avoiding predators. Trilobites exhibited remarkable diversity throughout their reign. Scientists have identified over 20,000 species, ranging in size from less than a centimeter to giants reaching 75 centimeters in length. This diversity wasn't just in size. Trilobites occupied virtually every marine ecological niche. Some were bottom dwellers, plying through sediment for food, while others were active swimmers in the water column. Some species were filter feeders, others were predators, and some may have even formed symbiotic relationships with sulfur-oxidizing bacteria. What made trilobites particularly special was their ability to adapt and evolve in response to changing environments. They developed various defensive strategies, including the ability to roll into a ball when threatened, much like modern pillbugs. Many species evolved elaborate spines and protrusions that served as protection against predators. Their exoskeletons became increasingly complex over time, with some developing intricate patterns and textures that likely served both defensive and sensory functions. The success of trilobites is also evident in their reproductive strategies. Like modern arthropods, they grew through a series of molts, shedding their exoskeletons as they increased in size. This process has left us with abundant fossils, not just of complete specimens, but also of their molted shells, providing paleontologists with valuable information about their growth and development. Trilobites were also among the first animals to develop sophisticated social behaviors. Some species have been found fossilized in groups, suggesting they may have gathered in large numbers for protection or reproduction, similar to modern marine arthropods. Their track fossils, known as trace fossils, provide evidence of complex behavioral patterns, including feeding strategies and migration routes. But what led to their ultimate demise? The extinction of trilobites wasn't sudden but occurred gradually over millions of years. The rise of new predators, particularly jawed fishes, put increasing pressure on trilobite populations. Climate changes and shifting ocean chemistry also played crucial roles. The final blow came during the Permian-Triassic extinction event, the largest mass extinction in Earth's history, which wiped out approximately 95% of marine species, including the last remaining trilobites. The legacy of trilobites extends far beyond their extinction. Their abundant fossils serve as excellent index fossils, helping geologists date rock layers and understand ancient environments. Their evolution and adaptation strategies provide valuable insights into how species respond to environmental changes over long periods. The study of trilobites has contributed significantly to our understanding of evolutionary processes, ancient ecosystems, and the history of life on Earth. Perhaps most importantly, trilobites remind us of the dynamic nature of life on our planet. Their 270 million year reign demonstrates both the potential for long-term evolutionary success and the inevitability of change in Earth's history. They adapted to countless environmental changes, survived multiple mass extinctions, and only succumbed to the most severe crisis in marine life's history. What lessons can we learn from these ancient arthropods? Their story teaches us about resilience, adaptation, and the importance of diversity in ensuring long-term survival. As we face modern environmental challenges, the trilobite's tale serves as both a reminder of life's resilience and a warning about the limits of adaptation in the face of rapid environmental change. The study of trilobites continues to yield new insights, with researchers using advanced technologies to understand their biology, behavior, and evolution better. Each new discovery adds another chapter to their remarkable story, helping us better understand not just these fascinating creatures, but the very history of life on Earth. Have you ever wondered what it would be like to encounter a shark the size of a school bus? Imagine swimming in ancient oceans and coming face to face with the most formidable predator that ever ruled the seas, the Megalodon. This incredible creature, whose scientific name Osaurus Megalodon means giant tooth, dominated the world's oceans for an astounding period of about 20 million years. Let's dive deep into the fascinating world of this prehistoric super predator. The Megalodon existed from approximately 23 to 3.6 million years ago during the early Miocene to the Pliocene epochs. But just how big was this ancient shark? Adult megalodons reached lengths of up to 60 feet, 18 meters, and weighed as much as 70 tons. To put this into perspective, that's about 3 times longer than the largest great white sharks we know today. One of the most remarkable features of the Megalodon was its teeth. These weren't just any ordinary teeth, they were massive, serrated weapons that could grow up to 7 inches, 18 centimeters, in length. Scientists have discovered thousands of these fossilized teeth across the globe, from North America to Australia. Each tooth was designed for a specific purpose in the shark's hunting strategy. The front teeth were perfect for grabbing and piercing, while the back teeth were ideal for sawing through tough flesh and bone. But what made Megalodon such an effective predator? The answer lies in its hunting strategies and physical adaptations. Unlike modern sharks, Megalodon had a much more robust skeleton, particularly around its jaw and vertebral column. This reinforced structure allowed it to generate incredible bite force, estimated at between 108,514 to 182,201 newtons. For comparison, a modern great white shark's bite force is about 18,216 newtons. What did this ancient super predator eat? Megalodons were apex predators that primarily targeted large marine mammals. Their diet included prehistoric whales, seals, and other large fish. Fossil evidence shows that they particularly favored attacking the bony, nutrient-rich areas around their prey's hearts and lungs. Scientists have found whale bones with distinctive Megalodon bite marks, providing direct evidence of these hunting patterns. Did you know that baby Megalodons were already larger than adult humans when they were born? Researchers estimate that newborn Megalodons were about 6.6 feet, 2 meters, long. These young sharks likely spent their early years in special nursery areas, similar to modern sharks, where they could grow and develop their hunting skills in relative safety. The Megalodon's hunting technique was particularly sophisticated. Using its powerful tail fin, it could swim at speeds estimated around 11 meters per second, allowing it to ambush prey from below. The shark would first disable its large prey by crushing their fins or flippers with its powerful bite, preventing escape, before delivering the fatal blow. What led to the extinction of this magnificent creature? The answer lies in a combination of factors. Around 3.6 million years ago, global cooling led to sea level changes that affected the warm water coastal areas Megalodons preferred. This climate change coincided with the evolution of new prey species that were faster and more agile, making them harder to catch. Additionally, The emergence of new predators, including the ancestor of modern killer whales, created competition for food resources. Another fascinating aspect of Megalodon's existence was its global distribution. Fossil evidence shows that these sharks lived in virtually all coastal waters that were warm enough to support them. They were particularly abundant in areas that are now the Americas, Europe, Africa, and Australia. This wide distribution suggests they were highly adaptable predators capable of surviving in various marine environments. The legacy of Megalodon continues to influence our understanding of marine ecosystems and predator-prey relationships. Their existence proves that the ocean once supported much larger predators than it does today, raising important questions about marine ecosystem evolution and climate change impacts on ocean life. How do we know so much about an animal that went extinct millions of years ago? While soft tissues don't typically fossilize, Megalodon left behind numerous clues about its existence. Besides their distinctive teeth, scientists have found fossilized vertebrae, coprolites, fossilized droppings, and trace fossils such as bite marks on prey species. By studying these remains and comparing them with modern sharks, researchers have been able to reconstruct much of Megalodon's biology and behavior. The study of Megalodon continues to yield new insights. Recent research has revealed that these sharks may have been even larger than previously thought, and their hunting strategies more complex than initially believed. Some scientists now think they may have hunted in family groups, similar to modern killer whales, though this remains a topic of debate in the scientific community. The story of Megalodon serves as a reminder of the incredible diversity of life that has existed on our planet and the dramatic ways in which climate change can affect even the most successful species. It also highlights the importance of understanding prehistoric life in helping us comprehend current marine ecosystems and their potential future changes. Have you ever picked up a spiral-shaped fossil on a beach or in the mountains and wondered about its story? These beautiful spiral shells belong to one of the most successful groups of marine animals that ever lived, the ammonites. For nearly 350 million years, these fascinating creatures ruled the ancient seas, evolving into thousands of species before their eventual extinction alongside the dinosaurs. Let's dive into the remarkable story of these prehistoric cephalopods, cousins to today's octopuses, squids, and nautiluses. The ammonite's tale begins in the Devonian period, around 400 million years ago, when they first emerged from their smaller shelled ancestors. But what made these spiral-shelled creatures so special? The secret to ammonite's success lay in their sophisticated shell design. Their shells weren't just protective homes, they were engineering marvels that allowed these creatures to achieve perfect buoyancy in the water. The spiral shell was divided into numerous chambers separated by walls called septa. As the ammonite grew, it would create a new, larger chamber and move into it, sealing off the previous one. These empty chambers formed a natural buoyancy system similar to the ballast tanks in modern submarines. The complexity of their shells tells us even more about their lives. The distinctive suture patterns, the lines where the septa meet the outer shell, became increasingly complex over millions of years of evolution. These intricate patterns weren't just for show, they strengthened the shell, allowing ammonites to dive deeper without their shells imploding under pressure. Think about it, how many modern animals have evolved such an elegant solution to deep-sea survival? But ammonites weren't just passive floating creatures. They were active predators, using their tentacles to catch prey much like modern squid do. Their shells could range from smaller than a coin to the size of a truck tire, with the largest known species, Parapusosia sepinrodensis, reaching a diameter of 2.5 meters. Imagine encountering such a creature while swimming in the ancient seas. What made ammonites truly remarkable was their diversity. They evolved into countless shapes and sizes, adapting to different marine environments and ecological niches. Some developed spines for protection, others flattened shells for life near the seafloor, and some even developed shells that uncoiled into irregular shapes. This adaptability helped them survive multiple mass extinctions throughout their long reign. Ammonites became so abundant and widespread that today they serve as index fossils, geological timestamps that help scientists date rock layers and understand Earth's history. Their rapid evolution and distinctive shells make them perfect markers for specific time periods. When you find an ammonite fossil, you're not just holding an ancient shell, you're holding a key to understanding Earth's past. But what made these successful creatures finally disappear? The answer lies in one of Earth's most dramatic events, the same catastrophe that ended the age of dinosaurs 66 million years ago. The Cretaceous-Paleogene extinction event, triggered by a massive asteroid impact, brought the ammonites' long reign to an end. While their shelled cousin, the Nautilus, managed to survive, the ammonites couldn't adapt to the rapidly changing conditions. The extinction of ammonites teaches us valuable lessons about survival and adaptation. Despite their incredible success and diversity, they couldn't overcome the sudden global changes that followed the asteroid impact. The warming oceans, acidification, and disruption of the food chain proved too much for these ancient mariners. Today, we find ammonite fossils on every continent, including mountains that were once ancient seabeds. Their presence in unexpected places helps us understand how Earth's geography has changed over millions of years. How did marine fossils end up on mountain tops? The answer lies in the powerful forces of plate tectonics, which have lifted ancient seabeds to great heights. The legacy of ammonites continues to influence science and culture. Their perfect spiral shells have inspired mathematicians studying natural geometry, architects designing spiral structures, and artists capturing the beauty of natural forms. Their fossils have been collected and valued by humans for thousands of years, often featured in folklore and traditional medicine. The story of ammonites reminds us that even the most successful species can face extinction when environmental changes occur too rapidly for evolution to keep pace. Their rise and fall parallel many other great dynasties in Earth's history, where groups of organisms dominated for millions of years before disappearing forever. As we face modern environmental challenges, what lessons can we learn from the ammonite story? Their extinction reminds us of the delicate balance in Earth's ecosystems and how sudden changes can have far-reaching consequences. While ammonites no longer swim in our oceans, their fossilized remains continue to teach us about Earth's past and the importance of adaptation in the face of environmental change. The next time you encounter an ammonite fossil, remember that you're holding evidence of an empire that ruled the seas for hundreds of millions of years. These spiral shells tell a story of evolutionary success, adaptation, and ultimately, extinction, a reminder of the constant change that shapes life on Earth. Have you ever wondered what it would be like to encounter a fish the size of a great white shark, covered in armor plates, with a bite force that could snap a small carp in half? Meet Dunkleosteus, one of the most formidable predators that ever swam in Earth's oceans during the late Devonian period, approximately 382 to 358 million years ago. Let's begin with what made Dunkleosteus truly extraordinary. Unlike modern fish that have scales and bones, Dunkleosteus belonged to a group called Placoderms, which were armored fish characterized by bony plates that covered their head and thorax. But what made this creature particularly fascinating wasn't just its armor, it was its incredible jaw mechanism. Imagine two sharp, bony blades instead of teeth. These blades weren't actually teeth in the conventional sense, but rather extensions of its skull plates that developed into sharp, self-sharpening cutting edges. When scientists studied the biomechanics of Dunkleosteus's jaw, they discovered something astounding. It could exert an estimated bite force of 8,000 pounds per square inch at the tip of its fang-like plates and up to 11,000 pounds per square inch at the blade-like joints of the jaw. To put this into perspective, that's stronger than the bite force of any modern-day fish and rivals that of Tyrannosaurus rex. But why did Dunkleosteus need such powerful jaws? The answer lies in its role as an apex predator in the Devonian seas. This period is often called the Age of Fishes because of the incredible diversity of fish species that evolved during this time. Dunkleosteus needed to be able to crack through the hard shells and armor of other sea creatures, including other placoderms, ammonites, and early sharks. The hunting strategy of Dunkleosteus was particularly interesting. Based on fossil evidence and studies of its jaw mechanics, scientists believe it was capable of opening its mouth in just 50 milliseconds, creating a powerful suction force that would have helped draw prey into its deadly jaws. This rapid jaw movement would have created a vacuum effect, similar to what modern-day fish like groupers use to catch their prey. Size was another factor that made Dunkleosteus terrifying. The largest species, Dunkleosteus torelli, could grow up to 20 feet, 6 meters, in length and likely weighed around 1 to 4 tons. Its head alone was protected by armor plates up to 2 inches thick. Think about that. This was a fish with armor plating thicker than some modern military vehicles. What's particularly fascinating about Dunkleosteus is how it processed its food. Unlike modern predatory fish that can swallow their prey whole or tear off chunks, Dunkleosteus had to rely on its powerful jaw plates to slice and crush its food. Evidence suggests it may have been one of the first vertebrates to actually chew its food, marking an important evolutionary development in feeding mechanisms. The impact of Dunkleosteus on its ecosystem was profound. As an apex predator, it would have played a crucial role in controlling populations of other marine species, helping to maintain the balance of Devonian marine ecosystems. However, this powerful predator wasn't invincible. Like many other species, it faced extinction at the end of the Devonian period during what scientists call the Hagenberg event, a mass extinction that wiped out many marine species. What made Dunkleosteus particularly unique in the history of evolution was its armor-plated design. While most modern fish have evolved to be streamlined and flexible, Dunkleosteus represented a different evolutionary strategy, one that favored heavy armor and overwhelming bite force. This strategy proved successful for millions of years, but ultimately came to an end with the Devonian extinction event. The legacy of Dunkleosteus continues to influence our understanding of prehistoric marine ecosystems. Its fossils, particularly well-preserved skull plates, found in locations like the Cleveland Shale in Ohio, which is why it was named after Cleveland Natural History Museum curator David Dunkel, provide valuable insights into the evolution of jawed vertebrates and predator-prey relationships in ancient seas. The study of Dunkleosteus also raises interesting questions about convergent evolution. Its powerful bite force and predatory lifestyle are similar to those of much later marine predators, suggesting that certain hunting strategies and adaptations have repeatedly evolved throughout Earth's history when similar ecological niches become available. Perhaps most intriguingly, Dunkleosteus shows us that nature has experimented with different forms of predatory fish design over millions of years. While modern sharks with their cartilaginous skeletons and replaceable teeth represent one successful evolutionary strategy, Dunkleosteus represented an alternative approach with its solid armor and blade-like jaw plates. This helps us understand that evolution doesn't always follow a straight path, but rather explores various solutions to survival challenges. In conclusion, Dunkleosteus stands as a testament to the incredible diversity of life that has existed on our planet. Its combination of massive size, unprecedented bite force, and unique armor plating made it one of the most formidable predators in Earth's history. While its kind may have vanished millions of years ago, studying this remarkable creature continues to provide valuable insights into the evolution of marine life and the complex dynamics of prehistoric ecosystems. Let's dive into one of the most fascinating marine reptiles that ever lived, the ichthyosaur. Have you ever wondered what would happen if you combined the speed of a dolphin, the hunting prowess of a tuna, and the birth-giving abilities of modern marine mammals? Nature already created such a creature about 250 million years ago. Ichthyosaurs, whose name literally means fish lizard, first appeared during the early Triassic period and survived until the late Cretaceous period, spanning an impressive 150 million years. But what makes these ancient marine reptiles so special? Unlike their predecessors, like the Dunkleosteus we discussed earlier, ichthyosaurs represented something entirely new. They were air-breathing reptiles that returned to the sea and evolved to become perfectly adapted to marine life. Let's break down their remarkable adaptations. First, consider their body shape. While their ancestors were land-dwelling reptiles, ichthyosaurs evolved a streamlined, fish-like body that bears an uncanny resemblance to modern dolphins and tuna. This wasn't a coincidence. It's a perfect example of convergent evolution, where different species evolve similar features to adapt to similar environments. Their smooth, torpedo-shaped body allowed them to slice through water with minimal resistance, making them incredibly efficient swimmers. One of the most remarkable features of ichthyosaurs was their eyes. Did you know they had the largest eyes relative to body size of any known animal in history? Some species, like Temnodontosaurus, had eyes the size of dinner plates, about 26 centimeters in diameter. These massive eyes allowed them to hunt effectively in deep or murky waters, giving them a significant advantage over their prey. Speaking of hunting, ichthyosaurs were formidable predators. Their long, pointed snouts were filled with numerous sharp teeth, perfect for catching slippery prey like fish and squid. Some species had hundreds of teeth, while others developed specialized teeth for crushing hard-shelled prey. Their powerful tail fin, shaped like a crescent moon, provided the thrust needed for quick bursts of speed to catch their prey. But perhaps one of the most fascinating aspects of ichthyosaurs was their reproductive strategy. Unlike most reptiles, which lay eggs, ichthyosaurs gave birth to live young in the water. Fossil evidence shows that they gave birth tail first, just like modern whales and dolphins, to prevent the babies from drowning during delivery. Multiple fossils have been found with embryos inside the mother's body cavity, and some even captured the moment of birth, an extraordinary snapshot of ancient life. Their breathing apparatus was equally impressive. As air-breathing reptiles living in water, they developed blowholes similar to those of modern whales, positioned near the top of their heads. This adaptation allowed them to breathe while remaining mostly submerged, making them more efficient predators. Ichthyosaurs also showed remarkable diversity in size. While some species were relatively small, around 1 to 2 meters in length, others grew to be giants. Shastosaurus, one of the largest known ichthyosaurs, reached lengths of about 21 meters, longer than a modern sperm whale. This size range allowed different species to occupy various ecological niches in the ancient oceans. Another fascinating aspect of ichthyosaurs was their probable warm-bloodedness. Evidence suggests they maintained a high metabolic rate and could regulate their body temperature, similar to modern tuna and marine mammals. This adaptation would have allowed them to swim faster and hunt more effectively in different water temperatures. The end of the ichthyosaur story is somewhat mysterious. Despite their successful adaptation to marine life, they disappeared from the fossil record about 90 million years ago, well before the mass extinction that killed the dinosaurs. Scientists believe changes in ocean chemistry, competition from other marine predators like sharks and mosasaurs, and changes in their prey populations might have contributed to their extinction. The legacy of ichthyosaurs lives on in our understanding of evolution. They demonstrate how thoroughly a land-dwelling animal can adapt to life in the water, developing features we see in modern marine animals. Their fossils, found on every continent, tell us stories about ancient ocean ecosystems and the incredible adaptability of life on Earth. From their specialized eyes to their streamlined bodies, from their live birth capabilities to their diverse sizing, ichthyosaurs represent one of nature's most successful experiments in returning to the sea. They remind us that the history of life on Earth is full of remarkable transformations and adaptations, each telling its own story of survival and evolution. As we close this chronicle of the ichthyosaurs, consider this. What other amazing adaptations might we discover as we continue to unearth fossils from Earth's ancient oceans? The story of these remarkable marine reptiles shows us that nature's capacity for innovation knows no bounds, and there are likely many more fascinating discoveries waiting to be made. When we think about prehistoric marine predators, our minds often drift to the massive sharks or the fearsome plesiosaurs. However, there's another group of marine reptiles that dominated the late Cretaceous seas, the mosasaurs. Have you ever wondered what could make even the mighty sharks of the time think twice before attacking? Let's dive into the fascinating world of these marine lizards that ruled the oceans during the final chapter of the dinosaur era. Mosasaurs weren't just any marine reptiles, they were specialized lizards that returned to the sea. Unlike the ichthyosaurs we discussed earlier, which had millions of years to perfect their fish-like form, mosasaurs were relatively recent converts to marine life when they first appeared around 98 million years ago. They were actually closely related to modern-day monitor lizards and snakes. Can you imagine a Komodo dragon adapting to life in the ocean? That's essentially what happened with mosasaurs. What made mosasaurs particularly fascinating was their incredible diversity and rapid evolution. From their first appearance in the fossil record, they quickly diversified into numerous species, ranging from the smaller cladests, about the size of a dolphin, to the enormous Mosasaurus hoffmanni, which could reach lengths of up to 17 meters. That's longer than a modern-day bus. But how did they become so successful in such a relatively short time? The answer lies in their remarkable adaptations. Unlike their land-dwelling lizard ancestors, mosasaurs developed several key features that made them excellent swimmers. Their limbs evolved into powerful flipper-like paddles, and their tails developed a distinctive downward bend that supported a large fin, similar to modern sharks. These adaptations allowed them to move through the water with both power and precision. But perhaps their most striking feature was their deadly arsenal of teeth. Mosasaurs had double-hinged jaws, similar to snakes, which allowed them to swallow large prey whole. Their teeth were curved and sharp, perfect for gripping slippery prey like fish and squid. Some species even developed crushing teeth specialized for cracking through the hard shells of ammonites and sea turtles. Think about that for a moment. These were lizards that could crush turtle shells as easily as we crack nuts. The hunting abilities of mosasaurs were equally impressive. They were active predators, using their excellent vision to spot prey in the ancient seas. Their eyes were positioned on the sides of their heads, providing good peripheral vision, and they likely had enhanced underwater vision similar to modern marine reptiles. But how did they navigate the dark depths of the ocean? Scientists believe that mosasaurs, like modern whales and dolphins, may have used their sense of hearing to detect prey underwater. Fossil evidence suggests they had adaptations in their ear structure that would have allowed them to hear underwater effectively. They might have also possessed specialized organs to detect pressure changes in the water, similar to the lateral line system in fish. One of the most fascinating aspects of mosasaur biology was their method of reproduction. Unlike many other marine reptiles that had to return to land to lay eggs, fossil evidence suggests that mosasaurs gave birth to live young in the water. This adaptation allowed them to become fully marine animals, never needing to return to land. Imagine these powerful predators caring for their young in the ancient seas. The diversity of mosasaurs was remarkable. Different species evolved to fill various ecological niches. Some were specialized for hunting in shallow coastal waters, while others ventured into the open ocean. Some species developed adaptations for diving deep into the ocean, while others remained near the surface. This ability to adapt and specialize helped mosasaurs become the dominant marine predators of their time. However, their reign would not last forever. Along with the dinosaurs and many other species, mosasaurs went extinct during the Great Mass Extinction event at the end of the Cretaceous period, approximately 66 million years ago. The same event that spelled doom for T-Rex and Triceratops also brought an end to these mighty marine lizards. The legacy of mosasaurs lives on in our understanding of evolution and adaptation. They demonstrate how quickly and effectively animals can adapt to new environments when the right conditions and opportunities present themselves. Their story also reminds us that even the most successful and dominant species can be vulnerable to global catastrophes. Today, mosasaur fossils continue to provide valuable insights into the ancient marine world. New discoveries are constantly adding to our knowledge of these fascinating creatures. For instance, recent findings have revealed details about their skin texture, showing that they had small, overlapping scales similar to those of modern snakes, rather than the larger scales of typical lizards. Understanding mosasaurs helps us piece together the complex puzzle of marine ecosystem evolution and reminds us of the incredible diversity of life that has existed on our planet. Their story is a testament to the remarkable adaptability of life and the constant changes that have shaped our world throughout its history. As we continue to study these magnificent creatures, what other secrets might they reveal about life in the ancient seas? When we think of penguins today, we typically picture the familiar black and white waddling birds that rarely exceed waist height. But did you know that millions of years ago, penguins were a very different story? Let's embark on a fascinating journey to explore the world of prehistoric penguin giants that once roamed our planet. During the Paleocene and Eocene epochs, approximately 66 to 34 million years ago, massive penguins ruled the southern oceans. The most remarkable of these ancient species was Cambrian, discovered in New Zealand and described in 2023. This incredible bird stood at an estimated height of 1.7 meters, 5 feet 7 inches, and weighed around 150 kilograms, 330 pounds. That's about the size of an adult human. But what made these prehistoric penguins grow to such impressive sizes? Scientists believe several factors contributed to their gigantism. After the extinction event that wiped out the dinosaurs, many marine predator niches were left vacant. This created an opportunity for penguins to evolve into larger sizes without facing significant competition. The absence of large marine mammals during this period also played a crucial role, as whales and seals had not yet evolved into their modern forms. Another fascinating giant penguin species was Anthroponis nordenskjöldii, which lived approximately 45 to 37 million years ago in Antarctica. This species reached heights of about 1.8 meters, 6 feet, and likely weighed over 90 kilograms, 200 pounds. Unlike modern penguins, these ancient giants had longer, more slender beaks and were probably more efficient swimmers due to their larger size and specialized wing structures. The discovery of Plesiosaurus klukowskii in Antarctica, dubbed the Colossus penguin, provides further evidence of prehistoric penguin gigantism. Based on bone fragments, scientists estimate this species could have reached heights of up to 2 meters, 6.5 feet, and weighed as much as 115 kilograms, 254 pounds. Can you imagine encountering a penguin taller than most basketball players? What made these ancient penguins particularly interesting was their adaptation to aquatic life. Unlike their modern counterparts, fossil evidence suggests they had longer wings proportional to their body size, making them powerful swimmers. Their bones were also more dense, allowing them to dive deeper and stay underwater longer while hunting for prey. The diet of these prehistoric giants likely consisted of fish and squid, similar to modern penguins, but their larger size meant they could tackle bigger prey and dive deeper into the ocean. Scientists estimate that some species could hold their breath for up to 40 minutes, giving them ample time to hunt in deeper waters. One might wonder, why aren't penguins this large today? The answer lies in climate change and competition. As the Earth's climate began cooling around 30 million years ago, the evolution of modern marine mammals like seals and whales created new competition for food resources. These mammals were better adapted to cold waters and could compete more effectively for the same prey items. Additionally, smaller penguin species proved more energy efficient in colder waters as their reduced body size required less food to maintain. The fossil record of these giant penguins provides valuable insights into their evolution and extinction. Most specimens have been found in New Zealand, Antarctica, and South America, indicating that the southern hemisphere was a crucial region for penguin evolution. The rocks where these fossils are found also tell us about the environmental conditions these birds lived in, suggesting warmer waters than what we associate with modern penguins. Recent discoveries continue to expand our understanding of prehistoric penguin diversity. In 2017, scientists announced the discovery of Cambrian in New Zealand, another giant species that lived around 60 million years ago. This finding helped establish that penguin gigantism evolved relatively quickly after the extinction of the dinosaurs. The study of prehistoric penguin giants also helps us understand how climate change affects marine species. As our current climate continues to warm, modern penguins face numerous challenges. By studying how their ancient relatives adapted to different environmental conditions, we might better understand how today's penguins might respond to changing environments. The legacy of these prehistoric giants lives on in the 18 species of modern penguins we see today. While they may be smaller, modern penguins have evolved to be incredibly efficient in their current ecosystems. The emperor penguin, the largest living species, stands at about 1.2 meters, 4 feet, tall, impressive, but still significantly smaller than their ancient relatives. Understanding prehistoric penguin giants helps us appreciate the remarkable adaptability of life on Earth. These birds represent a fascinating chapter in evolutionary history, demonstrating how species can dramatically change in response to environmental opportunities and challenges. As we continue to uncover new fossils and develop better research techniques, who knows what other secrets about these magnificent creatures we might discover. The story of prehistoric penguin giants reminds us that the natural world is full of surprises and that the animals we know today may be very different from their ancient ancestors. It raises intriguing questions about evolution, adaptation, and the future of species in our changing world. Have you ever wondered how whales, those magnificent marine mammals we know today, evolved from land-dwelling creatures? The story of Basilosaurus and the evolution of whales is one of the most fascinating transitions in the history of life on Earth, showcasing how a group of mammals returned to the sea. Let's start with Basilosaurus itself, whose name ironically means king lizard because its fossils were initially mistaken for a reptile. Living approximately 40 to 34 million years ago during the late Eocene epoch, Basilosaurus represents one of the earliest fully aquatic whales. But how did we get there? The journey from land to sea is a remarkable tale of adaptation and survival. The story begins roughly 50 million years ago with a group of wolf-sized, hoofed mammals called pachycetids. These early whale ancestors lived near the edges of shallow waters in what is now Pakistan and India. They were predominantly land animals but spent time near water hunting for food. Their ear structures already showed early adaptations for underwater hearing, providing the first clues of their eventual aquatic destiny. Following the pachycetids came the Ambulocetus, often called the walking whale. This creature, about the size of a large sea lion, had strong legs that could support it on land, but also webbed feet that made it an efficient swimmer. Picture a creature that moved like an otter on land but could swim with the grace of a modern seal. This represents a crucial intermediate stage in whale evolution, showing how these animals were becoming increasingly adapted to an aquatic lifestyle. The next major step came with proboscideans, who developed more streamlined bodies and tail-powered swimming abilities. Their nostrils began migrating backward on their snouts, starting the long journey that would eventually lead to the blowholes we see in modern whales. These animals could still walk on land, but were spending more and more time in the water. Then came the Remingtonocids and Rhodhocitus, showing further adaptations to aquatic life. Their legs became shorter, their tails grew stronger, and their bodies became more streamlined. These changes made them more efficient swimmers, but less capable on land. It's fascinating to see how each evolutionary step brought these animals closer to the fully aquatic lifestyle we associate with modern whales. Finally, we arrive at Basilosaurus, one of the first fully aquatic whales. Unlike its predecessors, Basilosaurus could no longer support itself on land. Measuring up to 18 meters, 60 feet, in length, it had a serpentine body with tiny hind limbs that could no longer bear weight. These vestigial limbs are one of the most compelling pieces of evidence for whale evolution, showing their terrestrial heritage. Basilosaurus had several distinctive features that set it apart from both its ancestors and modern whales. It possessed small but sharp teeth, indicating it was a predator. Its elongated body was different from the more robust forms we see in modern whales, suggesting it might have swum with an eel-like motion rather than the up and down tail movements characteristic of modern cetaceans. The discovery of Basilosaurus fossils in what is now Egypt's Western Desert, an area that was once covered by an ancient ocean, helped scientists understand the transition of whales from land to sea. These fossils, along with those of other early whales, provide an almost complete evolutionary sequence showing how whales adapted to life in the water. What makes this evolutionary journey even more remarkable is the speed at which it occurred. In just about 10 million years, whales transformed from land-dwelling mammals to fully aquatic creatures, a relatively short time in evolutionary terms. This rapid transition was likely driven by the rich feeding opportunities in the ocean and the relative safety from predators that the aquatic environment provided. The story of Basilosaurus and early whale evolution teaches us several important lessons about evolution. First, it shows that major transitions can occur through a series of intermediate steps, each providing advantages in their own right. Second, it demonstrates how structures can be repurposed, legs becoming flippers, nostrils becoming blowholes. Finally, it reminds us that the fossils we find are often just snapshots of much longer evolutionary processes. Today, Modern whales retain various features that hint at their terrestrial ancestry. They still have arm-like flippers with finger bones inside, vestigial hip bones, and they must surface to breathe air with lungs just like their land-dwelling ancestors. They even maintain the same basic mammalian body temperature regulation and give birth to live young, nursing them with milk, all inheritances from their terrestrial past. The story of Basilosaurus and early whale evolution continues to captivate scientists and the public alike, serving as one of the best documented examples of a major evolutionary transition. It reminds us that the natural world is constantly changing, and the creatures we see today are the result of millions of years of evolutionary adaptation and survival. Welcome to one of the most fascinating chapters in Earth's prehistoric history, the realm of Liopleurodon, a marine apex predator that ruled the Jurassic seas approximately 166 to 155 million years ago. Have you ever wondered what it would be like to encounter a predator so massive that it could make today's great white sharks look small in comparison? Liopleurodon belonged to a group called Plesiosaurs, which were part of the larger Plesiosaur family. These remarkable marine reptiles weren't dinosaurs at all, but rather a completely different lineage that had adapted perfectly to life in the ancient oceans. What made Liopleurodon particularly spectacular? Let's dive into its extraordinary characteristics. First, let's address its size. While early estimates suggested lengths of up to 25 meters, more recent scientific studies indicate that Liopleurodon typically reached lengths of 6 to 7 meters, with some exceptional specimens possibly growing up to 10 meters. Even at these more modest dimensions, Liopleurodon was still one of the largest predators of its time. Its skull alone could measure up to 1.8 meters in length, equipped with massive jaws lined with large conical teeth that could reach 20 centimeters in length. The name Liopleurodon means smooth-sided teeth, referring to the distinctive dental characteristics that helped paleontologists identify and classify this creature. But what made these teeth so effective? Unlike the serrated teeth of sharks, Liopleurodon's teeth were designed for gripping and crushing, perfect for catching slippery prey like fish, squid, and even other marine reptiles. One of the most remarkable features of Liopleurodon was its advanced sensory capabilities. Like modern sharks, it possessed large nostrils located near the snout tip, suggesting an excellent sense of smell. This adaptation would have been crucial for detecting prey from considerable distances in the murky Jurassic waters. Can you imagine a predator so well adapted that it could smell its prey from dozens of meters away? The body design of Liopleurodon was a masterpiece of natural engineering. It had 4 powerful flipper-like limbs that could generate tremendous thrust, allowing it to achieve short bursts of high speed when pursuing prey. These flippers, combined with its streamlined body shape, made Liopleurodon an incredibly efficient swimmer. The creature's body was teardrop-shaped, reducing water resistance and allowing it to move through the water with minimal energy expenditure. But what about its hunting strategy? Paleontologists believe Liopleurodon was an ambush predator, using its powerful sensory abilities to detect prey before launching swift, powerful attacks. Its large eyes suggest it had excellent vision, which, combined with its sense of smell, made it a formidable hunter in both clear and murky waters. The ecosystem where Liopleurodon lived was the Jurassic Ocean, a very different environment from today's seas. During this period, the world's oceans were warmer and sea levels were higher, creating vast shallow seas that became perfect hunting grounds for these marine predators. The waters were teeming with various species of fish, squid, ammonites, and other marine reptiles, providing Liopleurodon with a diverse menu of prey items. What evidence do we have of Liopleurodon's existence? Fossils have been found in several locations across Europe, particularly in England and France. These fossils include not just teeth and skull fragments, but also more complete skeletal remains that have helped scientists understand its anatomy and lifestyle. The Oxford Clay Formation in England has been particularly rich in Liopleurodon fossils, providing valuable insights into these magnificent creatures. The impact of Liopleurodon on its ecosystem was significant. As an apex predator, it would have played a crucial role in maintaining the balance of Jurassic marine ecosystems. By controlling the populations of other marine creatures, it helped maintain the health and diversity of ancient ocean communities. This role is similar to that played by today's great white sharks and orcas. Understanding Liopleurodon helps us appreciate the incredible diversity of life that has existed on our planet. How did such a magnificent creature evolve? What led to its eventual extinction? These questions continue to drive paleontological research today. The study of Liopleurodon and its relatives provides valuable insights into the evolution of marine reptiles and the ways in which animals adapt to life in the oceans. The legacy of Liopleurodon extends beyond its physical remains. It has captured the public imagination through various documentaries and educational programs, helping us understand the magnificent creatures that once ruled our planet's oceans. Its study continues to contribute to our understanding of marine reptile evolution, prehistoric ocean ecosystems, and the incredible diversity of life that has existed throughout Earth's history. Liopleurodon's realm was a world of incredible biodiversity and evolutionary innovation, where these magnificent marine reptiles reigned supreme as the ocean's top predators. Their story reminds us of the amazing creatures that have come before us and the constant change that characterizes life on Earth. What other secrets might the fossils of these ancient marine predators still hold? The investigation continues as scientists work to uncover more details about these fascinating creatures that once ruled the Jurassic seas. Welcome to one of the most peculiar and fascinating creatures that ever swam in our ancient oceans, the Helicoprion. Have you ever wondered what would happen if nature decided to experiment with dental arrangements? Well, this remarkable ancient shark-like fish did exactly that, sporting what might be the most unusual set of teeth in the history of vertebrate evolution. Helicoprion lived approximately 290 to 250 million years ago during the Permian period, long before the dinosaurs ruled the Earth. What makes this creature truly extraordinary isn't just its shark-like appearance, but rather its bizarre lower jaw arrangement, a spiral of teeth that has puzzled scientists for over a century since its first discovery. Let's start with the most striking feature, the tooth wall. Imagine a circular saw blade made entirely of teeth, coiled up like a roll of tape. This is essentially what Helicoprion carried in its lower jaw. But why was this arrangement so unique? Unlike modern sharks that regularly lose and replace their teeth, Helicoprion kept all its old teeth, which continued to grow in a spiral pattern throughout its life. The newest, sharpest teeth were positioned at the front of the hall, while older teeth rotated backward and inward, creating this remarkable spiral structure. When the first Helicoprion fossils were discovered in the late 1800s, scientists were completely baffled. They had never seen anything like it before. Some initially thought the spiral might have been an external defense mechanism, like a shell. Others suggested it could have been mounted on the snout like a saw. It wasn't until recent decades, with the help of advanced imaging techniques and better preserved specimens, that we began to understand how this unusual dental arrangement actually worked. The size of these tooth walls could be impressive, with some specimens suggesting the animal could grow to lengths of 20 to 25 feet, 6 to 7.5 meters. The individual teeth within the hall could reach sizes of up to 3.5 inches, 9 centimeters, indicating these were formidable predators of their time. But how did Helicoprion use this bizarre tooth arrangement to feed? This question has intrigued paleontologists for generations. Recent studies suggest that the tooth hole functioned as an efficient feeding mechanism. When Helicoprion opened its mouth, the newest teeth at the front of the hole would have slashed through prey like a curved blade. As the jaw closed, the spiral arrangement would have helped to pull prey further into the mouth, while also slicing it into smaller, more manageable pieces. What's particularly fascinating about Helicoprion is what it tells us about survival and adaptation. This unusual dental arrangement wasn't just a random mutation, it was successful enough to persist for around 40 million years. That's longer than the entire existence of many other prehistoric species. This success suggests that, despite its bizarre appearance, the tooth hole was an effective hunting adaptation. The prey of Helicoprion likely consisted mainly of soft-bodied creatures like ancient squid and other cephalopods. The spiral tooth arrangement would have been particularly effective at grabbing and processing these slippery prey items. Think about trying to eat spaghetti with a spiral tool. It would be much more effective than using straight implements. Another fascinating aspect of Helicoprion is what it tells us about the diversity of ancient marine life. While we often think of evolutionary adaptations as gradually becoming more conventional over time, Helicoprion shows us that nature sometimes takes unexpected turns. This creature existed at a time when life on Earth was recovering from the largest mass extinction in history, the end Permian extinction, and its unique adaptation represents one of the many evolutionary experiments that emerged during this period of recovery. The study of Helicoprion also demonstrates how our understanding of prehistoric life continues to evolve with new technologies and discoveries. For many years, scientists could only speculate about how the tooth hole functioned, but modern CT scanning and 3D modeling have allowed us to better understand its mechanics and role in feeding. What makes Helicoprion particularly relevant to modern science is what it teaches us about adaptation and survival. In an ever-changing world, sometimes the most unusual adaptations can prove successful. This ancient creature reminds us that evolution doesn't always follow predictable paths, and what might seem bizarre to us could be a perfectly viable survival strategy. Today, while we don't see anything quite like Helicoprion's spiral tooth hole in modern oceans, its legacy lives on in our understanding of marine predator evolution and the incredible diversity of life that has existed on our planet. It stands as a testament to nature's capacity for innovation and the endless possibilities of evolutionary adaptation. As we continue to study and understand creatures like Helicoprion, we're reminded of how much we still have to learn about Earth's prehistoric past. What other unusual adaptations might we discover as we continue to unearth fossils from ancient seas? How many more surprising innovations might nature have experimented with over the millions of years of life's history on Earth? The story of Helicoprion serves as a humbling reminder that what we might consider normal or standard in nature is really just a snapshot of what's possible. In the grand scheme of evolution, the unusual and bizarre might be more common than we think. Let's dive into one of the most formidable marine predators that ever patrolled Earth's ancient oceans, the Kronosaurus. Have you ever wondered what would happen if you combined the strength of a killer whale with the length of a bus and the bite force that could crush a small boat? Well, that's what we're about to explore. The Kronosaurus, named after Kronos, the leader of the Greek Titans, was a massive marine reptile that lived during the early Cretaceous period, approximately 125 to 99 million years ago. But what makes this creature particularly special is its strong connection to Australia, where some of the most complete fossils have been discovered. Imagine swimming in the ancient Australian seas. What would it feel like to encounter this apex predator? Let's start with the facts about its size, which are truly impressive. The Kronosaurus reached lengths of up to 10 to 11 meters, 33 to 36 feet, making it one of the largest plesiosaurs ever discovered. Its skull alone measured up to 2.7 meters, 9 feet, in length. To put this in perspective, that's longer than most modern-day cars. The massive head housed rows of large conical teeth, some reaching lengths of 30 centimeters, 12 inches. But what truly set Kronosaurus apart from other marine predators was its unique body structure. Unlike the long-necked plesiosaurs, Kronosaurus had a relatively short neck and a massive skull, which made up about a quarter of its total body length. This design wasn't by accident, it was perfectly adapted for its hunting strategy. The large skull housed powerful jaw muscles that could generate tremendous bite force, while its 4 powerful flipper-like limbs allowed it to accelerate quickly through the water to catch prey. Speaking of prey, what did this massive predator eat? Paleontological evidence suggests that Kronosaurus was an apex predator that fed on a variety of marine creatures. Its diet included large fish, marine reptiles, including other plesiosaurs, ancient squid, and possibly even smaller members of its own species. Bite marks found on fossil specimens of other marine creatures from this period bear testament to its predatory nature. The discovery history of Kronosaurus is particularly fascinating. The first remains were found in the early 1920s in Queensland, Australia. But it wasn't until 1931 that the genus was formally named by Harry Wilfred Longman. One of the most complete specimens was discovered in 1932 by an expedition from Harvard University, also in Queensland. This specimen now stands as a mounted skeleton in Harvard's Museum of Comparative Zoology. The Australian connection doesn't end there. The geological formation where most Kronosaurus fossils have been found is called the Great Artesian Basin, particularly in the Toolbuck Formation. During the early Cretaceous period, this region was covered by a vast inland sea, creating perfect conditions for these marine reptiles to thrive. The waters were warm, relatively shallow, and teeming with prey. An ideal kingdom for such a powerful predator. What made Kronosaurus such a successful predator? Its hunting strategy was likely similar to modern-day killer whales. The powerful flippers provided the thrust needed for quick bursts of speed, while its streamlined body reduced water resistance. The positioning of its eyes on the sides of its head provided excellent peripheral vision, crucial for detecting prey in the open ocean. But perhaps its most fearsome feature was its bite force. Studies suggest it could have been one of the most powerful of any known animal. The extinction of Kronosaurus, like many other marine reptiles, coincided with significant changes in Earth's oceans during the late Cretaceous period. Rising sea levels, changing ocean temperatures, and shifts in prey availability likely contributed to their eventual disappearance. However, their legacy lives on in the fossil record, providing us with valuable insights into the diversity of life during the age of dinosaurs. One of the most intriguing aspects of Kronosaurus is how it challenges our understanding of marine reptile evolution. Unlike dinosaurs, which evolved from land-dwelling ancestors, Kronosaurus belonged to a group of reptiles that returned to the sea. This evolutionary journey resulted in numerous adaptations that made them perfectly suited for marine life, from their flipper-like limbs to their streamlined bodies. The study of Kronosaurus continues to yield new insights. Recent research has focused on understanding their metabolism, swimming capabilities, and role in ancient marine ecosystems. Questions still remain about their social behavior, breeding habits, and the full extent of their distribution across the ancient oceans. Were they solitary hunters, or did they hunt in groups? Did they have specific breeding grounds? These are questions that continue to drive paleontological research. In conclusion, Kronosaurus represents a fascinating chapter in Earth's prehistoric past. Its reign in the ancient Australian seas demonstrates the incredible diversity of life that has existed on our planet. As we continue to uncover new fossils and apply new technologies to study them, our understanding of these magnificent creatures grows, helping us piece together the complex puzzle of life's evolution in Earth's oceans. As we venture from the fierce Kronosaurus into another remarkable creature of the ancient seas, we encounter one of the most fascinating marine reptiles that ever existed, the archalan. But what made this prehistoric sea turtle so special? Why does its very name command attention in paleontological circles? Archalan, whose name literally means ruling turtle in Greek, was the largest sea turtle that ever lived. This incredible creature swam in the waters of what is now North America during the late Cretaceous period, approximately 80 to 65 million years ago. To truly appreciate its magnitude, consider this. While today's largest sea turtle, the leatherback, can reach lengths of up to 6 feet, archalan grew to an astounding length of 13 feet from head to tail. Its shell alone measured about 8 feet in length, and the entire animal could weigh up to 4,900 pounds. But what truly sets archalan apart wasn't just its size, it was its unique armor. Unlike modern sea turtles with their solid, bony shells, archalan's shell had a fascinating structural adaptation. The shell was relatively light and had large spaces between the ribs, covered by thick leather-like skin. Why would such a massive creature have a lighter shell structure? This design served multiple purposes. It reduced the turtle's overall weight, making it more buoyant and allowing for more efficient swimming, while still providing protection against predators. The question that often arises is, how did archalan feed with such a massive body? Its beak was incredibly powerful and hooked, perfectly adapted for crushing the hard shells of its prey. The main items on archalan's menu included mollusks, squid, jellyfish, and other soft-bodied sea creatures. Its jaw muscles were exceptionally strong, allowing it to crack open the shells of various marine creatures with ease. One of the most intriguing aspects of archalan was its habitat and lifestyle. These magnificent creatures lived in the Western Interior Seaway, a vast body of water that split North America into two landmasses during the Cretaceous period. This warm, shallow sea provided perfect conditions for these giant turtles to thrive. The majority of archaean fossils have been found in what is now South Dakota, giving us crucial insights into their distribution and environment. But how did these massive turtles reproduce? Like modern sea turtles, female archaeans would have had to drag their enormous bodies onto land to lay eggs. Given their immense size, this would have been an incredibly strenuous task, requiring tremendous strength and determination. The nesting sites would have been on the beaches of the Western Interior Seaway, where the females would dig nests and lay their eggs in the warm sand. The evolution of archaean presents a fascinating story of adaptation and survival. What drove these turtles to evolve to such enormous sizes? Scientists believe that their size was an adaptation to the dangerous seas they inhabited. During the late Cretaceous, the oceans were home to numerous predators, including mosasaurs and large sharks. Being larger meant better defense against these predators and the ability to dive deeper and stay underwater longer. Another remarkable feature of archaean was its endurance and swimming ability. Despite its massive size, it was an efficient swimmer, using its powerful flippers to propel itself through the water. These flippers were proportionally larger than those of modern sea turtles, allowing for powerful swimming strokes. The front flippers could span up to 16 feet from tip to tip, making them incredibly effective for long-distance travel. The extinction of archaean coincided with the Great Cretaceous Paleogene extinction event that wiped out the dinosaurs about 66 million years ago. What makes their story particularly poignant is that while they disappeared, their smaller relatives survived and evolved into the sea turtles we know today. This raises interesting questions about the advantages and disadvantages of extreme size in survival through major extinction events. What can we learn from archaean's existence? Their success as a species for millions of years demonstrates the effectiveness of their adaptations. The balance they achieve between protection and mobility through their unique shell structure shows how evolution can produce remarkable solutions to survival challenges. Their existence also helps us understand the diversity of life that once inhabited our oceans and how modern sea turtles evolved. The study of archaean continues to yield new insights into prehistoric marine life. Each fossil discovery adds to our understanding of these magnificent creatures and the world they inhabited. Their legacy lives on not only in the fossil record, but also in what they teach us about adaptation, survival, and the incredible diversity of life that has existed on our planet. As we reflect on archaean's remarkable features, its size, unique armor, feeding adaptations, and survival strategies, we gain a deeper appreciation for the complexity and wonder of prehistoric life. These ancient mariners remind us that the history of life on Earth is filled with extraordinary creatures that push the boundaries of what we think is possible in terms of size and adaptation. Let's dive into one of the most fearsome predatory fish that ever roamed the ancient seas, the Typhectinus. Have you ever wondered what it would be like to encounter a fish the size of a large car, with fangs as long as your fingers? That's exactly what we're about to explore. Typhectinus, often called the X-fish due to its challenging name pronunciation, Typhectinus, was a massive predatory fish that lived during the late Cretaceous period, approximately 85 to 70 million years ago. But what made this creature so remarkable? First and foremost, its size was absolutely stunning. Reaching lengths of up to 18 feet, 5.5 meters, Typhectinus was one of the largest predatory fish of its time. To put this in perspective, that's about the length of a modern-day great white shark. The most distinctive feature of Typhectinus was its terrifying set of teeth. Unlike modern fish that might have rows of similar-sized teeth, Typhectinus had large, fang-like teeth that protruded from its jaws even when its mouth was closed. These weren't just any teeth, they were sharp, curved, and could grow up to several inches in length. But why did it need such impressive dental equipment? The answer lies in its hunting strategy. Typhectinus was an active predator, and fossil evidence gives us remarkable insights into its feeding habits. One of the most famous Typhectinus fossils, discovered in Kansas, USA, contains something extraordinary: a complete 6-foot-long fish preserved inside its body cavity. This fossil, known as the fish within a fish, provides direct evidence that Siphectinus was capable of swallowing prey almost half its own length. Can you imagine a modern fish attempting such a feat? The anatomy of Siphectinus was perfectly adapted for its predatory lifestyle. Its streamlined body, powerful tail fin, and large, upward-facing eyes made it an efficient hunter. The fish had a bulldog-like face with a slightly upturned snout, giving it a distinctively fierce appearance. Its body was covered in large, diamond-shaped scales that provided protection while allowing for quick movement through the water. But where did Siphectinus live? During the late Cretaceous period, much of North America was covered by a vast inland sea called the Western Interior Seaway. This shallow marine environment, which split North America into two landmasses, was Siphectinus's hunting ground. Fossil remains have been found throughout this region, particularly in Kansas, which was once at the bottom of this ancient sea. What made Siphectinus such a successful predator? Besides its impressive size and fearsome teeth, it possessed several advantages. Its large eyes suggested it was a visual hunter, possibly able to spot prey from considerable distances. The fish's powerful swimming muscles and streamlined shape allowed it to achieve burst speeds when attacking prey, similar to modern-day tuna. However, life wasn't always easy for Siphectinus. Fossil evidence shows that these fish often engaged in violent confrontations. Many specimens show signs of healed injuries, suggesting they frequently fought with their own kind or other large marine predators. Some fossils even show bite marks that match the tooth pattern of other Siphectinus, indicating these fish may have been cannibalistic. The extinction of Siphectinus coincided with the end Cretaceous mass extinction event approximately 66 million years ago. This was the same event that wiped out the non-avian dinosaurs. But why did this powerful predator fail to survive? Like many marine species, Siphectinus was likely affected by the dramatic changes in ocean chemistry and temperature that followed the asteroid impact at the end of the Cretaceous period. What can we learn from Siphectinus today? This ancient predator provides valuable insights into the evolution of large marine predators and the complex ecosystems of prehistoric seas. Its fossils help us understand how predator-prey relationships worked in ancient oceans and how marine life has changed over millions of years. The legacy of Siphectinus lives on in modern museums, where its impressive fossils continue to captivate visitors. The next time you see a large modern predatory fish like a tuna or barracuda, remember that they had much larger and more fearsome relatives in the ancient seas. Siphectinus stands as a testament to the incredible diversity of life that has existed on our planet and reminds us that today's oceans, while still home to impressive predators, are quite different from those of the Cretaceous period. What would it have been like to witness a Siphectinus attack in the ancient seas? While we can never know for certain, the fossil evidence paints a picture of a swift, powerful predator that could take on prey nearly its own size. It's a reminder that the history of life on Earth is filled with remarkable creatures that push the boundaries of what we think is possible in nature. When we think of sloths today, we picture slow-moving creatures hanging upside down in trees, lazily munching on leaves. But did you know that millions of years ago, there were sloths that took to the seas? Let's dive into the fascinating story of Plesiosaurus, a remarkable genus of ancient sloths that broke all the rules we associate with these animals today. Plesiosaurus lived during the late Miocene to late Pliocene epochs, approximately 7 to 3 million years ago, along the western coast of South America, particularly in what is now Peru and Chile. Their discovery revolutionized our understanding of sloth evolution and adaptability. But what makes these marine sloths so special? Unlike their modern tree-dwelling relatives, Plesiosaurus developed remarkable adaptations for an aquatic lifestyle. These sloths underwent a gradual evolutionary transition from terrestrial to marine life, a process documented through multiple species spanning several million years. This transformation presents one of the most well-documented cases of evolutionary adaptation in the fossil record. The earliest species of Plesiosaurus were likely shore-dwelling animals that fed on coastal vegetation. Over time, successive species showed increasing adaptations for an aquatic lifestyle. Their bones became denser to help them stay underwater, similar to modern marine mammals. Their limbs evolved to become more efficient for swimming, with their front legs developing into powerful paddle-like appendages. But what drove these sloths to take to the water? The answer lies in their environment. During the late Miocene, the western coast of South America was characterized by arid conditions. The rich marine ecosystem offered more reliable food sources than the sparse terrestrial vegetation. Thalassocnus evolved to exploit marine plants, particularly seagrasses and algae growing in shallow coastal waters. The anatomy of Thalassocnus reveals fascinating details about their lifestyle. Their snouts became increasingly narrow over time, an adaptation that likely helped them better grasp and consume marine vegetation. Their teeth developed specialized features for processing tough marine plants, different from both their terrestrial ancestors and modern sloths. One of the most intriguing aspects of Thalassocnus is how they moved in the water. Unlike modern marine mammals that use their tails for propulsion, these marine sloths primarily use their powerful forelimbs to swim, similar to modern sea lions. Their hind limbs remained strong and were likely used for walking on the seafloor and moving on land, making them truly amphibious creatures. The different species of Thalassocnus show a clear evolutionary progression. Thalassocnus antiquus, the earliest known species, showing initial adaptations to coastal life. Thalassocnus natans developed more aquatic adaptations. Thalassocnus littoralis showed further specialization for marine life. Thalassocnus corollomartini had even more advanced aquatic features. Thalassocnus yosensis, the most derived species with the strongest adaptations for marine life. This evolutionary sequence occurred over approximately 4 million years, showing how quickly animals can adapt to new environments when there are strong environmental pressures and available ecological niches. The extinction of Thalassocnus coincided with significant environmental changes along the South American coast. Climate change and shifting ocean currents likely affected their food sources and habitat. Additionally, the emergence of new marine mammal competitors might have played a role in their disappearance. What makes the Thalassocnus story particularly valuable to science is how it demonstrates convergent evolution, where unrelated species develop similar features in response to similar environmental pressures. Many of their aquatic adaptations parallel those seen in other marine mammals, despite their very different ancestral origins. The discovery of Thalassocnus also challenges our assumptions about the capabilities and adaptability of different animal groups. Who would have thought that members of a group we associate with slow movement and tree-dwelling could become successful marine animals? Their fossil record provides important insights into how animals adapt to changing environments and exploit new ecological niches. This has particular relevance today as we study how modern species might respond to climate change and environmental pressures. Thalassocnus represents more than just an interesting prehistoric animal. It's a testament to the incredible adaptability of life on Earth. These marine sloths remind us that evolution can take unexpected turns, producing remarkable creatures that challenge our preconceptions about what certain animals can or cannot do. The study of Thalassocnus continues to yield new insights. Recent research has focused on understanding their diving capabilities, feeding mechanisms, and the specific environmental conditions that facilitated their evolution. Each new discovery adds another piece to the puzzle of these remarkable creatures. As we face current environmental challenges, the story of Thalassocnus offers valuable lessons about adaptation and survival. How did these animals successfully transition from land to sea? What can their story tell us about the potential for modern species to adapt to changing environments? These questions remain relevant as we study and work to protect modern marine mammals and their habitats. Let's embark on a fascinating journey back to the Middle Triassic period, roughly 240 to 210 million years ago, to explore one of the most intriguing marine reptiles that helped bridge the gap between terrestrial and aquatic life: the Nothosaurus. Have you ever wondered what the first steps of evolution from land to sea looked like? The Nothosaurus provides us with a remarkable example of this transition. Unlike the fully aquatic ichthyosaurs or plesiosaurs that would come later, Nothosaurus represents an intermediate stage in the evolution of marine reptiles. The name Nothosaurus means false lizard, but there was nothing false about its impressive adaptations. These creatures grew to lengths ranging from 1 to 4 meters, depending on the species, and possessed a unique combination of features that made them equally capable on both land and in water. Think of them as the ancient equivalent of seals or sea lions, animals that haven't fully committed to an aquatic lifestyle, but are nonetheless highly adapted to life in the water. Let's examine their physical characteristics in detail. Nothosaurus had a long, slender skull with numerous sharp teeth, perfect for catching slippery prey like fish. Their nostrils were positioned high on their snout, similar to modern crocodiles, allowing them to breathe while mostly submerged. But what made them truly special was their body structure. The limbs of Nothosaurus tell us a fascinating story about evolutionary adaptation. Their feet were webbed, making them excellent swimmers, but they retained strong claws that allowed them to move effectively on land. This dual adaptation suggests they likely spent time both in water hunting and on land, possibly for activities like basking in the sun or laying eggs. One of the most remarkable features of Nothosaurus was its sensory system. The snout was covered in small pits that housed sensitive nerve endings, similar to those found in modern crocodiles. These receptors would have allowed them to detect the movement of prey in water, making them efficient predators. Can you imagine how effective this would have been for hunting in murky Triassic waters? The vertebral column of Nothosaurus shows us clear signs of adaptation to an aquatic lifestyle. Their backbone was more flexible than that of purely terrestrial reptiles, allowing for the undulating swimming motion that would have propelled them through the water. However, it wasn't as specialized as later marine reptiles, supporting the idea that they were still in a transitional stage. Fossil evidence tells us that Nothosaurus was widespread during the Triassic period. Their remains have been found across Europe, China, and North Africa, indicating they inhabited the shallow seas of the Tethys Ocean. This distribution helps us understand the ancient geography and climate of Earth during this period. What did Nothosaurus eat? Based on their tooth structure and skull morphology, we know they were primarily piscivorous, fish-eating, but they likely also preyed on squid and other marine invertebrates. Their long, narrow jaws were perfect for snapping up fast-moving prey in the water. The reproductive biology of Nothosaurus presents an interesting question in paleontology. While we don't have direct evidence of their reproductive habits, their body structure suggests they likely needed to return to land to lay eggs, similar to modern sea turtles. This would have made them vulnerable during breeding seasons and may have influenced their behavior and distribution patterns. Understanding Nothosaurus helps us piece together the larger puzzle of marine reptile evolution. They existed at a crucial time when many reptile groups were beginning to exploit marine environments. Their success paved the way for later, more specialized marine reptiles like Plesiosaurs and Ichthyosaurs. The extinction of Nothosaurus coincided with the end of the Triassic period, but their legacy lives on in the fossil record. They demonstrate a crucial evolutionary principle. Major transitions don't happen overnight, but through a series of intermediate stages, each successful in its own right. What makes Nothosaurus particularly valuable to paleontologists is how it exemplifies evolutionary transition. Their fossils provide clear evidence of how vertebrates adapted to marine life, showing us that evolution often proceeds through functional intermediate stages rather than dramatic leaps. The study of Nothosaurus continues to yield new insights. Recent research has used advanced imaging techniques to study their bone structure, revealing details about their growth patterns and metabolism. These studies suggest they may have had an intermediate metabolism, not quite as active as modern marine mammals, but more active than typical reptiles. As we conclude our exploration of Nothosaurus, consider how their story reflects the broader patterns of evolution. They remind us that nature often finds success not in extremes but in compromise, in this case, between terrestrial and aquatic lifestyles. Their ability to thrive in both environments made them successful for millions of years and provides us with valuable insights into how modern marine vertebrates evolved. The story of Nothosaurus is more than just ancient history. It's a window into the processes that shape life on Earth, showing us how organisms adapt to new environments and how evolutionary transitions occur. What other secrets might these fascinating creatures still hold? As technology advances and new fossils are discovered, our understanding of these remarkable animals continues to grow. Let's dive deep into one of the most fascinating marine reptiles that ever graced our planet's oceans, the Shonosaurus. Have you ever wondered what it would be like to encounter a swimming reptile the size of a large bus? Well, that's exactly what we're about to explore. Shonosaurus popularis, first discovered in Nevada's fossil beds, represents a remarkable chapter in the evolution of marine reptiles. But what makes this creature so special? For starters, it was one of the largest ichthyosaurs known to science, reaching lengths of about 50 feet, 15 meters. Just imagine a creature longer than 3 cars lined up end to end. The story of Shonosaurus begins in the late Triassic period, approximately 237 to 227 million years ago. During this time, while dinosaurs were just beginning to diversify on land, the oceans were dominated by these massive marine reptiles. But how did we come to know about these incredible creatures? The discovery of Shonosaurus is tied to a remarkable location, Berlin Ichthyosaur State Park in Nevada, USA. Here's where the plot thickens. In the 1920s, the first fossils were unearthed, but it wasn't until the 1950s that scientists realized the true significance of these findings. The area has yielded numerous specimens, making it one of the most important ichthyosaur fossil sites in North America. What's particularly intriguing is that multiple individuals were found together, leading to fascinating questions about their behavior and social structure. Let's talk about the anatomy of Shonosaurus, which reveals much about its lifestyle and capabilities. Unlike its smaller ichthyosaur relatives, Shonosaurus had some unique features. Its skull was relatively small compared to its body size, equipped with a long snout filled with small, peg-like teeth. What does this tell us about its feeding habits? Scientists believe these teeth were perfect for catching soft-bodied prey like squid and fish. One of the most remarkable aspects of Shonosaurus was its body plan. Like other ichthyosaurs, it had evolved to become incredibly fish-like, despite being a reptile. Its limbs had transformed into paddle-like flippers, and it possessed a powerful tail fin that would have propelled it through the water with remarkable efficiency. But how did a reptile become so perfectly adapted to marine life? The answer lies in millions of years of evolution. Shonosaurus's ancestors were land-dwelling reptiles that gradually returned to the sea, much like whales would do many millions of years later. Over time, their bodies became streamlined, their limbs transformed into flippers, and they developed other adaptations for marine life, such as the ability to give birth to live young in water rather than laying eggs on land. Speaking of reproduction, the evidence suggests that Shonosaurus, like other ichthyosaurs, was viviparous, meaning they gave birth to live young. Fossil discoveries of pregnant ichthyosaurs have shown that these marine reptiles gave birth to well-developed offspring, ready to swim and hunt shortly after birth. Isn't it fascinating how these ancient marine reptiles had developed such advanced reproductive strategies? The environment in which Shonosaurus lived was vastly different from today's oceans. During the late Triassic, the area that would become Nevada was covered by a warm, shallow sea. This marine environment was rich in life, providing plenty of prey for these giant predators. But what led to their eventual extinction? Like many species from the late Triassic, Shonosaurus didn't survive into the Jurassic period. The end Triassic extinction event, one of the major mass extinctions in Earth's history, likely played a role in their disappearance. This event, marked by significant climate change and ocean acidification, reshaped marine ecosystems worldwide. The legacy of Shonosaurus continues to influence our understanding of marine reptile evolution. Their fossils provide crucial evidence about how reptiles can adapt to marine life, the diversity of marine ecosystems in the Triassic period, and the evolution of large marine predators. The study of these creatures helps us understand how modern marine animals might adapt to changing environments and what factors influence the success or failure of marine species. The importance of Shonosaurus extends beyond paleontology. It serves as a remarkable example of convergent evolution, where different groups of animals evolve similar features in response to similar environmental pressures. The fish-like body shape of Shonosaurus, which evolved independently from fish, would later be mirrored by other marine vertebrates like whales and dolphins. As we continue to study these fascinating creatures, new discoveries are constantly being made. Recent research has revealed more about their metabolism, swimming capabilities, and potential hunting strategies. Each new finding adds another piece to the puzzle of understanding these magnificent marine reptiles and their world. The story of Osaurus reminds us that life on Earth has taken many fascinating forms throughout its history. These ancient marine reptiles, with their remarkable adaptations and impressive size, continue to capture our imagination and drive scientific inquiry into the mysteries of life's past. Let's dive deep into one of the most fascinating predators that ever ruled Earth's ancient oceans, the mighty Pterygotus, a sea scorpion that would make modern scorpions look like tiny insects in comparison. Have you ever wondered what it would be like to encounter a scorpion the size of a human? Well, during the Paleozoic era, such creatures actually existed. Pterygotus belonged to a group called Eurypterids, commonly known as sea scorpions, though they weren't true scorpions as we know them today. These remarkable creatures lived approximately 470 to 370 million years ago during the Silurian and Devonian periods. But what made Pterygotus truly exceptional was its incredible size. Some species could grow up to 2.5 meters, 8.2 feet, in length, making them among the largest arthropods that ever existed. Let's break down what made Pterygotus such a formidable predator. Unlike modern scorpions, Pterygotus didn't possess a venomous stinger. Instead, it was equipped with massive, powerful claws called chelicera at the front of its body. These claws weren't just for show, they were serrated and could easily grip and tear apart prey. Think of them as nature's equivalent of serrated kitchen knives, but far more deadly and efficient. The body of Pterygotus was divided into three main sections: the prosoma, head, mesosoma, thorax, and metasoma, tail. The prosoma was covered by a large shield-like structure called the carapace, which contained compound eyes that gave these predators excellent vision. This visual acuity, combined with their size and powerful appendages, made them incredibly successful hunters in the ancient seas. One of the most interesting aspects of Pterygotus was its swimming capability. Unlike many other arthropods, Pterygotus had specialized paddle-like limbs that it used for swimming. These appendages were flattened and covered with fine hair-like structures that helped them move efficiently through the water. The last pair of legs was particularly modified into large, flat paddles that provided powerful forward thrust. But what did these massive sea scorpions eat? Pterygotus was an apex predator in its ecosystem, feeding on a variety of marine life, including early fish, other arthropods, and possibly even smaller members of its own species. Their fossilized remains have been found with evidence of predation marks on various prey items, giving us valuable insights into their feeding habits. The discovery of Pterygotus fossils has been particularly exciting for paleontologists. Some of the best preserved specimens have been found in places like Scotland, Estonia, and New York State, where ancient marine sediments have perfectly preserved these remarkable creatures. These fossils tell us not just about the animal's appearance, but also about the environments they lived in and their role in ancient ecosystems. What's particularly fascinating about Pterygotus is what it tells us about the evolution of arthropods. Today, the largest arthropods are much smaller than their ancient relatives. This raises interesting questions about why such giant forms existed in the past but not today. Scientists believe factors such as higher oxygen levels in the ancient atmosphere and different environmental conditions may have allowed arthropods to reach such impressive sizes. The extinction of Pterygotus and other large eurypterids coincided with the rise of jawed fishes. As these new predators evolved more sophisticated hunting strategies and better armor, the reign of the giant sea scorpions came to an end. This demonstrates how the evolution of new predators can dramatically reshape entire ecosystems. Understanding Pterygotus helps us appreciate the incredible diversity of life that has existed on our planet. It shows us that the largest arthropods alive today, like the Japanese spider crab or the giant centipede, are actually modest in size compared to their ancient relatives. It also reminds us that the history of life on Earth is filled with remarkable creatures that seem almost too extraordinary to have been real. The study of Pterygotus continues to yield new insights. Recent research has focused on understanding their locomotion, feeding mechanisms, and role in ancient food webs. Using modern technology like CT scanning and 3D modeling, scientists can now create detailed reconstructions of how these creatures moved and hunted. The legacy of Pterygotus lives on in our understanding of arthropod evolution and ancient marine ecosystems. These magnificent creatures remind us that the history of life on Earth is far more diverse and fascinating than we might imagine. They also serve as a testament to the incredible changes our planet has undergone over millions of years. So next time you see a modern scorpion or crab, remember their ancient relative Pterygotus, the giant sea scorpion that once ruled the Paleozoic seas. What other giant creatures might have existed in Earth's past that we haven't discovered yet? The search continues, and each new fossil discovery helps us better understand the amazing story of life on our planet. Let's dive into one of the most formidable marine predators that ever lived, the Tylosaurus. Have you ever wondered what would happen if you combined the hunting prowess of a modern killer whale with the size of a bus and the agility of a sea snake? That's essentially what we're dealing with when we talk about Tylosaurus, the ultimate mosasaur of the late Cretaceous period. Tylosaurus belonged to the family Mosasauridae, a group of marine reptiles that dominated the seas during the last part of the age of dinosaurs, specifically from about 85 to 80 million years ago. But what made Tylosaurus special among its relatives? For starters, it was absolutely massive. The largest specimens reached lengths of up to 15 meters, 49 feet, making it one of the largest mosasaurs ever discovered. The Western Interior Seaway, where Tylosaurus reigned supreme, was a vast body of water that split North America into two landmasses during the late Cretaceous. This shallow sea stretched from the Gulf of Mexico to the Arctic Ocean, creating a perfect hunting ground for these marine predators. The warm, nutrient-rich waters supported a diverse ecosystem that Tylosaurus exploited to its full advantage. Let's talk about its hunting equipment. Tylosaurus possessed a unique feature that set it apart from other mosasaurs, a long, pointed snout filled with two rows of powerful conical teeth. But what's particularly interesting is the short, blunt projection at the tip of its snout. Scientists believe this was used to ram prey, stunning them before delivering the killing bite. Think of it as a built-in battering ram. The hunting strategy of Tylosaurus was remarkably efficient. Unlike many other marine predators that specialized in specific prey, Tylosaurus was an opportunistic hunter. Fossil evidence shows that its diet included fish, sharks, smaller mosasaurs, plesiosaurs, and even seabirds that ventured too close to the water's surface. How do we know this? Remarkably preserved fossils have been found with the partially digested remains of these creatures in the stomach region. One of the most fascinating aspects of Tylosaurus was its adaptation to marine life. Despite being a reptile that evolved from terrestrial ancestors, it developed several specialized features for life in the water. Its body was streamlined, with a powerful tail that made up nearly half its length. The tail ended in a downturned fluke, similar to modern sharks, which provided powerful forward propulsion. The limbs of Tylosaurus had evolved into paddle-like flippers, perfect for maneuvering in water but useless on land. This tells us something important. Unlike modern sea turtles or seals, Tylosaurus never needed to return to land, not even for laying eggs. They were fully viviparous, giving birth to live young in the water, just like modern sea snakes and marine mammals. Another remarkable feature was its sensory capabilities. Tylosaurus had relatively large eyes with specialized adaptations for underwater vision. But perhaps more importantly, it possessed a row of sensory organs along its snout that could detect pressure changes in the water, similar to the lateral line system in fish. This gave it an additional advantage in detecting prey, even in murky waters or low light conditions. The discovery of Tylosaurus fossils has primarily occurred in the chalk deposits of Kansas, which was once covered by the Western Interior Seaway. These fossils have helped paleontologists understand not just the anatomy of these creatures, but also their behavior and ecosystem role. Some specimens show evidence of healing from severe injuries, suggesting they engaged in violent confrontations, possibly with their own kind. What ultimately led to the extinction of Tylosaurus? Like many other marine reptiles and dinosaurs, Tylosaurus disappeared during the mass extinction event at the end of the Cretaceous period, approximately 66 million years ago. The rapid changes in global climate and ocean chemistry, coupled with the aftermath of the Chicxulub asteroid impact, proved too much for these magnificent predators to survive. The legacy of Trilosaurus continues to fascinate scientists and the public alike. Its existence reminds us that the oceans of the past were home to creatures that rivaled or exceeded modern marine predators in size and hunting ability. The study of Trilosaurus has contributed significantly to our understanding of marine reptile evolution, prehistoric ocean ecosystems, and the diversity of life that existed during the age of dinosaurs. As we conclude our exploration of Trilosaurus, consider this. While we often focus on the terrestrial dinosaurs that ruled the land, the story of Trilosaurus reminds us that equally impressive dramas were playing out in the ancient seas. These marine reptiles were every bit as spectacular as their land-dwelling contemporaries, and their study continues to reveal new insights into the incredible diversity of life that has existed on our planet. Have you ever wondered what other massive predators roamed the ancient oceans alongside the famous Megalodon? While many are familiar with the enormous prehistoric shark, there's another equally fascinating marine giant that deserves our attention, the Leviathan melville. Let's dive into the remarkable story of this ancient sperm whale that once competed with Megalodon for ocean supremacy. Leviathan melville, named after the biblical sea monster Leviathan and Herman Melville, the author of Moby Dick, was discovered in 2008 in the Pisco Formation of Peru. The timing of this discovery opened up a whole new chapter in our understanding of prehistoric marine ecosystems. But what made this creature so special? Unlike modern sperm whales that primarily feed on squid in deep waters, Leviathan was built for hunting large prey near the surface. This massive creature lived approximately 9.9 to 8.9 million years ago during the Miocene epoch, sharing the oceans with Megalodon. Can you imagine two such enormous predators existing at the same time? Let's talk about size. Leviathan reached lengths of about 13.5 to 17.5 meters, 44 to 57 feet, making it similar in size to modern male sperm whales. However, what truly set it apart was its enormous skull and teeth. The skull alone measured up to 3 meters, 10 feet, in length, equipped with the largest functional teeth ever known in the animal kingdom. These teeth were massive, reaching up to 36.2 centimeters, 14.3 inches in length and about 12 centimeters, 4.7 inches in diameter. But why did Leviathan need such enormous teeth? Unlike modern sperm whales, this ancient predator was designed to hunt large marine mammals, including smaller whales, seals, and possibly even other marine predators. Its teeth weren't just for show, they were deadly weapons used to catch and kill prey. One of the most fascinating aspects of Leviathan was its hunting strategy. Scientists believe it used its powerful teeth and robust jaw muscles to deliver devastating bites to its prey, much like modern killer whales do today. But there's more. Leviathan also possessed a large spermaceti organ in its head, similar to modern sperm whales. This organ, filled with a waxy substance, likely helped in echolocation and deep diving, though perhaps not to the extreme depths that modern sperm whales reach. The competition between Leviathan and Megalodon must have been fierce. Both predators targeted similar prey species and occupied similar ecological niches. This situation, known as niche overlap, would have led to intense competition for resources. How did they manage to coexist? Scientists believe they might have developed different hunting strategies or preferred slightly different prey species to reduce direct competition. The environment where Leviathan lived was quite different from today's oceans. During the Miocene, the seas were warmer and filled with a diverse array of marine mammals, providing plenty of prey for large predators. The abundance of food likely supported the evolution of such massive predators. What led to Leviathan's extinction? While we don't have a definitive answer, scientists believe several factors contributed. Climate change during the late Miocene led to cooling oceans, which affected the distribution and abundance of prey species. Additionally, competition with other predators and changes in ocean circulation patterns might have played a role. The legacy of Leviathan continues to influence our understanding of marine evolution. Its existence shows us that sperm whales once filled different ecological roles than they do today. Modern sperm whales, though still impressive, are specialized deep-sea squid hunters, a far cry from their prehistoric relatives' role as an apex predator of large marine mammals. The discovery of Leviathan has also helped scientists better understand the diversity of ancient marine ecosystems. It demonstrates that multiple large predators could coexist in prehistoric oceans, suggesting these environments were incredibly productive and could support numerous apex predators. The story of Leviathan teaches us important lessons about evolution and adaptation. How do species evolve to fill specific ecological niches? What happens when multiple predators compete for similar resources? These questions continue to drive research in marine biology and paleontology. As we conclude our exploration of Leviathan's legends, we're left with a deeper appreciation for the diversity of life that has existed on our planet. This ancient whale serves as a reminder that the oceans of the past were very different from those we know today, filled with creatures that pushed the boundaries of what we thought possible in terms of size and predatory adaptation. The study of Leviathan continues to yield new insights, and who knows what other secrets about this magnificent creature might still be waiting to be discovered in the fossil record. Its story reminds us that there's still so much to learn about the prehistoric giants that once ruled our oceans. Let's dive deep into one of the most fascinating marine reptiles that ever lived, the Ophthalmosaurus, whose name literally means iron lizard. Have you ever wondered what it would be like to see perfectly in the darkest depths of the ocean? This remarkable creature from the late Jurassic period, approximately 165 to 150 million years ago, had that exact ability. The most striking feature of the Ophthalmosaurus was its enormous eyes, which were approximately 9.8 inches, 25 centimeters, in diameter, the largest eyes relative to body size of any known vertebrate. To put this in perspective, these eyes were about the size of dinner plates, and they played a crucial role in the animal's survival. But why did this creature need such massive eyes? The answer lies in the Ophthalmosaurus's hunting strategy and habitat. These marine reptiles were deep divers, regularly plunging into the darker zones of the Jurassic oceans in search of prey. Their giant eyes contained large amounts of rod cells, which are specialized for detecting light in low-light conditions. This adaptation allowed them to spot prey even in the dimly lit depths, where other predators would have been essentially blind. The structure of their eyes was supported by a ring of bony plates called the sclerotic ring, which helped maintain the eye's shape against the intense pressure of deep diving. This is a crucial piece of evidence that tells us about their diving capabilities, as similar structures are found in modern deep diving animals. But the Ophthalmosaurus's adaptations didn't stop at its eyes. The creature's body was perfectly streamlined for efficient swimming, reaching lengths of about 6 meters, 20 feet. Their bodies were torpedo-shaped, with a dolphin-like profile that helped them slice through the water with minimal resistance. Have you noticed how this body shape has evolved independently in many marine animals, from ancient to modern times? One of the most interesting aspects of Ophthalmosaurus was its specialized flipper structure. The front flippers contained many tightly packed finger bones, creating a rigid paddle that provided excellent maneuverability. This adaptation, combined with their powerful tail fin, made them incredibly agile swimmers, capable of chasing down fast-moving prey like squid and fish. The Ophthalmosaurus belonged to a group called the Ichthyosaurs, which means fish lizards. Despite their fish-like appearance, they were actually reptiles that returned to the sea, much like modern whales evolved from land-dwelling mammals. They gave birth to live young in the water, as evidenced by fossil specimens of mothers with babies preserved inside them or in the process of giving birth. Their teeth were relatively small and numerous, suggesting they fed primarily on soft-bodied prey like squid and small fish. The structure of their jaw and teeth indicates they were probably suction feeders, creating a vacuum to draw prey into their mouths, a feeding strategy still used by many modern marine animals. The brain of Ophthalmosaurus was also specially adapted for its lifestyle. The areas associated with vision were particularly well developed, as revealed by studies of their brain cases. This further supports the importance of sight in their hunting strategy and daily life. One fascinating aspect of their biology was their ability to regulate body temperature. Evidence suggests they may have maintained a body temperature higher than the surrounding water, similar to modern tuna and some sharks. This would have given them an advantage in pursuing prey and surviving in different water temperatures. Ophthalmosaurus fossils have been found across the world, from England to Argentina, indicating they were successful and widespread creatures. They lived during a time when the Earth's oceans were warmer and sea levels were higher than today, creating vast shallow seas perfect for these marine reptiles. The extinction of Ophthalmosaurus occurred before the end Cretaceous mass extinction that wiped out the dinosaurs. Their disappearance might have been related to changes in ocean conditions and competition from other marine predators, though the exact causes remain a matter of scientific debate. What makes the Ophthalmosaurus particularly special in paleontology is how much we know about its sensory capabilities. The exceptional preservation of numerous specimens has allowed scientists to understand not just their anatomy, but also how they perceived and interacted with their environment. Their giant eyes represent one of the most extreme adaptations ever evolved for vision in vertebrate history. The study of Ophthalmosaurus continues to provide insights into the evolution of marine reptiles and the adaptations necessary for life in the ancient oceans. Their remarkable eyes remind us that sometimes the most successful adaptations can be the most obvious ones, in this case, simply being able to see better than anyone else in the deep, dark ocean. Have you ever wondered what it would be like to encounter a creature with a neck longer than a giraffe's, swimming gracefully through ancient seas? The Elasmosaurus, one of the most remarkable marine reptiles of the late Cretaceous period, approximately 80.5 million years ago, presents us with exactly such a marvel. Let's begin with the most striking feature of this aquatic giant, its incredibly long neck. The Elasmosaurus possessed a neck containing 71 vertebrae, more than any other known vertebrate. To put this in perspective, most modern mammals, including humans, have only 7 neck vertebrae. This extraordinary neck measured about 7.1 meters, 23 feet, in length, which was longer than its entire body and tail combined. The total length of an adult Elasmosaurus reached approximately 14 meters, 46 feet. But why did the Elasmosaurus evolve such an unusually long neck? This question has intrigued paleontologists since its first discovery in Kansas, United States in 1868. The scientific consensus suggests that this anatomical feature served multiple purposes. The long neck allowed the Elasmosaurus to sneak up on schools of fish from below, using its neck like a submarine periscope to surprise its prey. The extended reach also enabled it to probe into crevices and coral reefs for hidden prey, much like modern-day herons use their long necks to catch fish in shallow waters. The discovery of the Elasmosaurus comes with an interesting historical footnote. When Edward Drinkercope, a prominent American paleontologist, first described the specimen in 1868, he made a significant error. He placed the skull on the wrong end of the vertebral column, attaching it to the tail instead of the neck. This mistake was later pointed out by his rival, Othniel Charles Marsh, leading to one of the most famous controversies in paleontology, known as the Bone Wars. Let's examine the Elasmosaurus's physical adaptations for marine life. Unlike ichthyosaurs, which evolved a fish-like body shape, plesiosaurs like Elasmosaurus maintained a more unique body plan. They possessed 4 large, paddle-like flippers that they used to fly through the water, similar to how sea turtles swim today. These flippers were powered by strong muscles attached to wide shoulder and hip girdles, allowing for efficient propulsion through the water. The creature's skull, though relatively small compared to its body size, was well equipped for catching prey. It contained numerous sharp, pointed teeth designed for gripping slippery fish and squid. The jaw muscles were strong enough to hold struggling prey, while the teeth's orientation helped prevent escape once caught. What did the Elasmosaurus eat? Based on fossil evidence and coprolites, fossilized droppings, we know their diet consisted primarily of fish, squid, and other marine organisms. Their feeding strategy likely involved using their long neck to approach prey from below or from a distance, striking quickly to catch their food. Some scientists suggest they might have also used their long necks to feed on bottom-dwelling creatures, though the neck's flexibility has been a subject of debate. The Elasmosaurus's habitat was the Western Interior Seaway, a vast body of water that split North America into 2 landmasses during the late Cretaceous period. This shallow sea provided ideal conditions for these marine reptiles, offering abundant prey and relatively warm waters. Fossil discoveries suggest they were well distributed throughout this region, with specimens found in Kansas, South Dakota, and other parts of Central North America. One fascinating aspect of Elasmosaurus biology was their method of reproduction. Like all plesiosaurs, they gave birth to live young rather than laying eggs. This conclusion is supported by fossil evidence of pregnant plesiosaurs and the fact that these creatures were too well adapted to marine life to come ashore for egg-laying. They likely gave birth to 1 or 2 large offspring, investing significant energy in each individual young, similar to modern whales and dolphins. The extinction of Elasmosaurus coincided with the end Cretaceous mass extinction event approximately 66 million years ago, the same event that wiped out the non-avian dinosaurs. This global catastrophe, triggered by a massive asteroid impact and subsequent environmental changes, brought an end to these remarkable marine reptiles after they had successfully inhabited Earth's oceans for millions of years. Understanding the Elasmosaurus helps us appreciate the incredible diversity of life that has existed on our planet. How did such a seemingly improbable body plan evolve and succeed for millions of years? What can these ancient marine reptiles teach us about adaptation and survival in changing environments? The Elasmosaurus continues to captivate scientists and the public alike, reminding us that truth can indeed be stranger than fiction in the natural world. As we continue to study these fascinating creatures through new fossil discoveries and advanced research techniques, we gain better insights into their lives and the ancient oceans they inhabited. The Elasmosaurus stands as a testament to the remarkable adaptability of life and the endless possibilities that evolution can produce. Let's embark on a fascinating journey through time to explore one of the most remarkable success stories in shark evolution, the Hybotis. Have you ever wondered how some species manage to survive multiple mass extinctions while others perish? The story of Hybotis provides compelling answers to this question. Hybotis, whose name means humped tooth, first appeared during the Permian period, approximately 260 million years ago, and persisted until the late Cretaceous period, about 85 million years ago. This incredible survival span of roughly 175 million years makes it one of the most enduring shark genera in Earth's history. But what made these sharks so special? The secret to Hybotis' success lay in its remarkable adaptability and versatile feeding strategy. Unlike many specialized predators that went extinct when their preferred prey disappeared, Hybotis was an opportunistic feeder. Its dental architecture tells us a fascinating story about its feeding habits. The shark possessed 2 distinct types of teeth, pointed ones for grabbing slippery prey like fish, and flatter, crushing teeth for handling hard-shelled creatures such as mollusks and crustaceans. This dual-purpose dentition allowed Hybotis to switch between different food sources when necessary, a crucial advantage during times of environmental stress. Physically, Hybotis sharks were moderate in size, typically reaching lengths of 2 to 3 meters, though some species grew larger. They possessed several distinctive features that set them apart from other sharks of their time. Most notably, they had 2 dorsal fins, each supported by a strong spine. These spines were not just for show, they served as defensive weapons against larger predators. The presence of these spines in the fossil record has helped paleontologists track the distribution and evolution of Hybotis across different time periods and locations. But what made Hybotis truly remarkable was its ability to survive multiple mass extinction events. The genus lived through the devastating Permian-Triassic extinction, the greatest mass extinction in Earth's history, the Triassic-Jurassic extinction, and continued well into the Cretaceous period. How did they manage this feat when so many other species perished? The answer lies in their habitat flexibility. Fossil evidence shows that Hybotis species could thrive in both marine and brackish waters. They were found in shallow coastal environments as well as deeper waters, indicating their ability to adapt to different marine conditions. This flexibility proved crucial during times of global crisis when many marine environments underwent dramatic changes. The success of Hybotis also teaches us important lessons about evolutionary adaptation. Their body plan represented a perfect balance between specialization and generalization. While they had specialized features like their distinctive dorsal spines and dual-purpose teeth, they weren't so specialized that they couldn't adapt when conditions changed. This middle ground approach to evolution proved to be a winning strategy. Another fascinating aspect of Hybotis was its global distribution. Fossils have been found across what were once the waters of Pangaea and later in the seas of multiple continents as they split apart. This widespread distribution suggests that Hybotis was highly successful in colonizing new environments and adapting to different regional conditions. The reproductive strategy of Hybotis, while not completely understood, likely contributed to their success. Like modern sharks, they probably produced relatively few well-developed offspring rather than numerous vulnerable ones. This strategy, combined with their adaptability, helped maintain stable populations over millions of years. Hybotis' reign finally came to an end in the late Cretaceous period, but their legacy lives on in the fossil record and in our understanding of successful evolutionary strategies. Their extinction coincided with significant changes in marine ecosystems and the rise of more modern shark groups, but their incredible 175 million year success story remains one of the most impressive in shark evolution. What makes the Hybotis story particularly relevant today is how it demonstrates the importance of adaptability in long-term survival. In an era when we're trying to understand how modern species might respond to environmental changes, the success story of Hybotis provides valuable insights into the characteristics that promote species survival over long time periods. The study of Hybotis continues to yield new insights. Recent fossil discoveries and advanced analytical techniques are helping us better understand their biology, behavior, and evolution. Each new finding adds another piece to the puzzle of how these remarkable sharks managed to persist for so long while other species came and went. In conclusion, the Hybotis story is more than just a tale of ancient sharks. It's a testament to the power of adaptability and the importance of maintaining a balance between specialization and generalization in evolution. Their success across multiple extinction events and varying environmental conditions offers valuable lessons for understanding species survival and adaptation in our changing world today. Let's dive deep into the fascinating world of one of the most remarkable marine reptiles that ever lived, the Temnodontosaurus. Have you ever wondered what it would be like to encounter a predator that combined the speed of a dolphin with the size of a bus and the bite force of a powerful crocodile? That's exactly what we're about to explore. Temnodontosaurus, whose name means cutting-tooth lizard, was one of the largest ichthyosaurs of the early Jurassic period, approximately 190 to 180 million years ago. But what made this creature so special? Let's unpack the extraordinary features of this marine giant. First, let's address the impressive size of this marine reptile. Temnodontosaurus could reach lengths of up to 9 meters, 30 feet, making it one of the apex predators of its time. Imagine a school bus swimming through ancient seas. That's roughly the size we're talking about. This massive size wasn't just for show, it served a crucial purpose in its survival and hunting strategies. The most distinctive feature of Temnodontosaurus was its enormous skull, which could measure up to 2 meters in length. Within this skull were powerful jaws lined with large conical teeth that were perfectly adapted for catching and crushing prey. But what's particularly interesting about these teeth? Unlike many other marine reptiles of its time, Temnodontosaurus had teeth that were not just sharp but also robust, allowing it to tackle a wide variety of prey. Speaking of prey, what did this massive predator eat? Temnodontosaurus was an active hunter that fed on a diverse menu including fish, squid-like creatures called belemnites, and even other marine reptiles. Fossil evidence suggests that it was capable of tackling prey almost as large as itself, making it a true apex predator of the early Jurassic seas. One of the most fascinating aspects of Temnodontosaurus was its eyes. Would you believe that it had some of the largest eyes relative to body size of any known animal? These eyes could reach up to 20 centimeters in diameter, about the size of a dinner plate. These massive eyes served a crucial purpose, allowing the creature to hunt effectively in deeper waters where light was limited. The body design of Temnodontosaurus was a masterpiece of natural engineering. Like other ichthyosaurs, it had a streamlined, fish-like body shape that was perfectly adapted for life in the water. Its powerful tail fin provided the main propulsion, while its paddle-like limbs helped with steering and stability. This design made it an incredibly efficient swimmer, capable of pursuing fast-moving prey and covering large distances. But how did Temnodontosaurus breathe? Like all ichthyosaurs, it was an air-breathing reptile that had to surface regularly to take in oxygen. However, its large size and efficient body design meant it could likely hold its breath for extended periods, allowing it to dive deep in search of prey. One of the most remarkable aspects of Temnodontosaurus was its reproductive biology. Like other ichthyosaurs, it gave birth to live young rather than laying eggs. Fossil evidence shows that these animals were viviparous, meaning they gave birth to well-developed offspring in the water. This adaptation eliminated the need to return to land for reproduction, allowing Temnodontosaurus to be fully adapted to marine life. The extinction of Temnodontosaurus marked the end of an era for large ichthyosaurs in the early Jurassic. While smaller ichthyosaurs would continue to thrive for millions of years afterward, the disappearance of these giants left a significant gap in the marine ecosystem. What caused their extinction? Scientists believe changes in global climate and ocean conditions, along with competition from other marine reptiles like Plesiosaurs, may have played a role. The legacy of Temnodontosaurus lives on in our understanding of marine reptile evolution. Its existence shows us how reptiles successfully adapted to life in the oceans, developing features that would later be mirrored by other marine animals like whales and dolphins. The convergent evolution we see in these creatures helps us understand how similar environmental pressures can lead to similar adaptations across different animal groups. The discovery and study of Temnodontosaurus fossils have been crucial in understanding the diversity of marine life during the Jurassic period. The first specimens were found in the early 19th century in England's Lyme Regis, and since then, numerous fossils have been discovered across Europe, providing us with a wealth of information about these magnificent creatures. What makes Temnodontosaurus particularly significant in the study of marine reptile evolution is its position as one of the early large ichthyosaurs. It represents a crucial stage in the development of these marine reptiles, showing how they evolved from smaller, more primitive forms to become dominant predators of the Jurassic seas. Let's dive into the fascinating world of Plesiosaurus, one of the most remarkable marine reptiles that dominated the late Cretaceous seas. Have you ever wondered what happened after the ichthyosaurs began to decline? As the mighty Temnodontosaurus and its relatives faded away, a new group of marine predators rose to prominence, the mosasaurs, and among them, Plesiosaurus was truly special. Plesiosaurus lived approximately 85 to 80 million years ago during the late Cretaceous period. This was a time when the world's oceans were very different from what we see today. North America was divided by a vast inland sea called the Western Interior Seaway, and this was where Plesiosaurus made its home. But what made this creature so remarkable? First, let's understand what Plesiosaurus actually was. It belonged to the mosasaur family, a group of marine reptiles that were actually closer relatives to modern monitor lizards and snakes than to dinosaurs. Imagine a creature about 4.3 meters, 14 feet, long, not the biggest mosasaur, but certainly no small fry either. But it's not just its size that made it interesting, it's how it lived and hunted that truly sets it apart. One of the most fascinating aspects of Plesiosaurus was its incredible swimming ability. Unlike its bulkier relatives, Plesiosaurus was built for speed and agility. Its body was streamlined with a long, powerful tail that ended in a downturned fluke, similar to modern sharks. This tail design wasn't just for show. It allowed Plesiosaurus to generate powerful forward thrust while maintaining excellent maneuverability. Think of it as the sports car of the Cretaceous seas. The skull of Plesiosaurus tells us a lot about its hunting strategies. It had a relatively short, robust skull compared to other mosasaurs, with rows of sharp conical teeth. These weren't the massive bone-crushing teeth of some other marine predators, but rather perfect tools for catching slippery prey like fish and squid. The positioning of its eyes on the sides of its head gave it excellent peripheral vision, crucial for spotting prey in the open ocean. But perhaps one of the most remarkable features of Plesiosaurus was its breathing apparatus. Recent fossil discoveries have shown that it had specialized blood vessels in its brain that helped regulate its body temperature and oxygen use. This adaptation allowed it to stay underwater for extended periods, making it an even more effective hunter. Isn't it amazing how evolution crafted such sophisticated solutions millions of years ago? Plate carpus also shows us something fascinating about mosasaur evolution. While earlier mosasaurs were probably more eel-like in their swimming style, plate carpus represents a more advanced form. Its body was more rigid and hydrodynamic, and its flippers were more efficiently designed for rapid swimming. This wasn't just a random change, it was part of a larger evolutionary trend that made mosasaurs increasingly better adapted to life in the open ocean. The environment where plate carpus lived was a dangerous but rich ecosystem. The western interior seaway was teeming with life, from tiny plankton to massive marine reptiles. Plate carpus occupied a middle-tier predator niche, feeding on smaller fish and squid, while itself potentially falling prey to larger mosasaurs like Trilobites. This complex food web shows us how diverse marine ecosystems were during the late Cretaceous. Fossil evidence of plate carpus has been found in several locations, but some of the best specimens come from the Niobrara Formation in Kansas. These fossils are so well preserved that they've allowed scientists to study not just the bones, but also soft tissue impressions. This has given us unprecedented insights into how these creatures looked and moved in life. Some specimens even preserve traces of their skin texture and internal organs. The end of plate carpus's reign came with the Great Cretaceous Paleogene extinction event about 66 million years ago. This same event that wiped out the non-avian dinosaurs also spelled doom for the mosasaurs. But during its time, plate carpus was a highly successful predator that had perfectly adapted to its marine environment. What makes plate carpus particularly important to paleontologists is how it helps us understand the evolution of marine reptiles. Its features show a perfect intermediate stage between more primitive mosasaurs and the most advanced forms. It's like a snapshot of evolution in action, showing how these remarkable creatures adapted to life in the open ocean. The study of plate carpus continues to yield new insights. Recent research has revealed details about its metabolism, swimming capabilities, and sensory abilities that we never knew before. Each new discovery helps us better understand not just this particular species, but the whole story of how reptiles returned to the sea and became such successful marine predators. As we reflect on plate carpus, we can appreciate how it represents a crucial chapter in the story of marine reptile evolution. It shows us how nature experiments with different body plans and adaptations, constantly refining and improving designs through natural selection. What other secrets might future discoveries about this fascinating creature reveal? Let's dive deep into the ancient waters of the Carboniferous period, about 360 to 290 million years ago, to meet one of the most impressive predatory fish that ever lived, the Rhizodus. Have you ever wondered what lurked in the waters before the age of dinosaurs? Well, prepare to be amazed by this massive load-finned fish that ruled the prehistoric waters. Rhizodus, whose name means root tooth, was truly a giant among its contemporaries. But what made this creature so remarkable? First, let's talk about its size. Imagine a fish reaching lengths of up to 7 meters, 23 feet. That's longer than a modern-day great white shark. This massive predator would have been one of the largest freshwater fish ever to exist, dominating the rivers and lakes of what is now Scotland and other parts of Europe and North America. The most distinctive feature of Rhizodus was its impressive set of teeth. Unlike many modern fish, Rhizodus had large, cone-shaped fangs that could grow up to 12 centimeters, 5 inches in length. These weren't just any teeth, they were deeply rooted in its jaws, similar to how our teeth are anchored in our gums, hence its scientific name. But why did it need such formidable dental equipment? The answer lies in its hunting strategy and the prey it pursued. As a member of the group known as Rhizodontids, Rhizodus belonged to an ancient lineage of load-finned fishes. But what exactly are load-finned fishes? They're a fascinating group that includes modern-day coelacanths and lungfish, characterized by muscular fins attached to the body by a single bone. This feature made them different from most modern fish, which have ray-finned fins. Think about that for a moment. Rhizodus was more closely related to our own ancestors than to most fish swimming in today's oceans. The Carboniferous period, when Rhizodus lived, was a time of great change on Earth. The atmosphere had higher oxygen levels than today, allowing arthropods and other creatures to grow to enormous sizes. The landscapes were dominated by vast swamps and forests of primitive trees, creating perfect conditions for the evolution of such a massive predator. These environmental conditions played a crucial role in shaping Rhizodus into the apex predator it became. But what did Rhizodus eat? With its size and powerful jaws, it would have been capable of tackling almost any prey in its environment. Fossil evidence suggests it fed on other fish, including smaller load-finned fish, early ray-finned fish, and possibly even some of the primitive amphibians that were beginning to venture onto land during this period. Its hunting strategy would have likely involved ambush attacks, using its powerful fins to launch quick strikes at unsuspecting prey. The anatomy of Rhizodus tells us even more about its lifestyle. Besides its impressive teeth, it had a robust skull reinforced to withstand the stresses of capturing and holding large, struggling prey. Its scales were thick and rhomboid-shaped, providing protection while allowing flexibility for quick movements. The structure of its fins suggests it was a powerful swimmer, capable of both sustained swimming and rapid bursts of speed when hunting. One of the most fascinating aspects of Rhizodus is what it tells us about the evolution of vertebrates. Remember those muscular, load-finned fins? They represent an important evolutionary stage in the development of limbs. The same basic bone structure that allowed Rhizodus to maneuver through carboniferous waters would later be modified in tetrapods, four-limbed vertebrates, to support weight on land. This makes Rhizodus not just an impressive predator, but also a window into our own evolutionary history. The extinction of Rhizodus, like many ancient species, coincided with significant environmental changes. As the Carboniferous period drew to a close, the vast swamps and forests that characterized this era began to change, affecting the entire ecosystem. This reminds us that even the mightiest predators are vulnerable to environmental change. What makes the study of Rhizodus particularly challenging is that, like many ancient fish, we primarily know it from fragmentary remains, mostly teeth, scales, and occasional bone fragments. Scientists must piece together these clues like a puzzle to understand its appearance and lifestyle. Each new fossil discovery adds another piece to our understanding of this remarkable creature. The legacy of Rhizodus lives on in the study of vertebrate evolution. Its existence demonstrates the incredible diversity of life that has existed on our planet and the amazing adaptations that organisms can develop. When we look at modern predatory fish, we can see echoes of the adaptations that made Rhizodus such a successful hunter in its time. Understanding creatures like Rhizodus helps us appreciate the complex history of life on Earth and the many forms it has taken over millions of years. It reminds us that the world we know today is just the latest chapter in a long story of evolution, extinction, and adaptation. What other secrets might still lie buried in the rocks, waiting to tell us more about these fascinating creatures from Earth's distant past? Let's dive into one of the most remarkable fossil discoveries that has helped us understand marine reptiles of the Mesozoic era, the Stenopterygius. Have you ever wondered what it would be like to find a fossil so well preserved that you could see not just bones, but actual soft tissues? That's exactly what makes Stenopterygius specimens so special. Stenopterygius was an ichthyosaur, a type of marine reptile that lived during the early Jurassic period, approximately 183 to 174 million years ago. But what makes this creature particularly fascinating isn't just its existence, but the exceptional quality of its fossils. The specimens found, particularly in Germany's Holzmaden Shale, have given us an unprecedented look at what these animals actually looked like in life, complete with skin impressions, muscle tissues, and even preserved body outlines. Why is soft tissue preservation so rare and important? Think about what typically happens when an animal dies. Soft parts usually decay quickly, leaving only hard parts like bones and teeth to fossilize. But under very special conditions, like those found in the Holzmaden Shale, even delicate tissues can be preserved. These conditions included fine-grained sediments and low-oxygen environments that prevented decay and allowed for exceptional preservation. The Stenopterygius fossils have revealed several crucial details about ichthyosaur biology that we wouldn't know otherwise. For instance, we can see the actual body shape of these animals, showing us that they had a more streamlined, dolphin-like form than we might have guessed from bones alone. The fossils show a distinctive dorsal fin and a crescent-shaped tail fin, features that would have been impossible to determine from skeletal remains alone. One of the most remarkable aspects of Stenopterygius fossils is what they've taught us about ichthyosaur reproduction. Several specimens have been found with embryos preserved inside their bodies, and others show juveniles that appear to have been in the process of being born. These fossils provided definitive evidence that ichthyosaurs gave birth to live young, rather than laying eggs like many other reptiles. They also showed that babies were born tail first, an adaptation that prevented them from drowning during birth, just like modern whales and dolphins. The size and proportions of Stenopterygius have been accurately determined thanks to these well-preserved specimens. They typically reached lengths of 2 to 3.5 meters, 6.5 to 11.5 feet, making them medium-sized ichthyosaurs. Their bodies were perfectly adapted for marine life, with powerful tail fins for propulsion and large eyes for hunting in dim light conditions. Speaking of hunting, the preserved stomach contents in some Stenopterygius specimens have given us direct evidence of their diet. They primarily fed on fish and squid-like creatures called belemnites, whose hard internal shells are often found as fossils themselves. The arrangement and shape of their teeth, combined with their large eyes, suggest they were active predators that could chase down their prey effectively. The skin impressions preserved in Stenopterygius fossils have revealed interesting details about their coloration and body covering. While we can't determine exact colors, the preservation shows patterns that suggest countershading, darker above and lighter below, a common adaptation in marine animals that provides camouflage from both predators and prey. These fossils have also helped us understand how ichthyosaurs move through the water. The preserved muscle structures and fin shapes indicate they were powerful swimmers that used their tails for propulsion, much like modern tuna or dolphins. This is a perfect example of convergent evolution, where different groups of animals develop similar adaptations to solve the same problems, in this case, efficient swimming. The Holzmatten Shale, where many of the best Stenopterygius specimens have been found, represents an ancient seabed from the Jurassic period. The exceptional preservation conditions there have given us a unique window into the past. But why are these fossils found there and not everywhere? The answer lies in the special conditions that existed in this ancient sea. Low oxygen levels, fine-grained mud, and rapid burial of dead animals all contributed to exceptional preservation. Understanding Stenopterygius helps us piece together the larger picture of marine ecosystem evolution. These creatures were part of a successful group that dominated the seas for millions of years, yet ultimately went extinct, while other marine reptile groups survived until the end of the Cretaceous period. What made them so successful for so long, and what ultimately led to their decline? These are questions that continue to intrigue paleontologists. The story of Stenopterygius reminds us that fossils aren't just old bones, they can preserve incredible details about ancient life when conditions are right. These specimens continue to be studied today, with new imaging techniques and analytical methods revealing even more details about these fascinating marine reptiles. They stand as testament to the remarkable preservation that can occur under the right conditions and continue to enhance our understanding of life in Earth's ancient oceans. Let's dive into the fascinating world of Plesiosaurus, a unique marine reptile that lived during the Triassic period, approximately 245 to 235 million years ago. Have you ever wondered what kind of creatures roamed the ancient seas before dinosaurs dominated the Earth? Plesiosaurus was one of these remarkable animals, and its story tells us much about the diversity of life in the Triassic oceans. Plesiosaurus, whose name literally means flat tooth, was perfectly adapted for a very specific dietary preference. But what made this creature so special? The answer lies in its distinctive dental arrangement and armor-like body structure. Unlike many other marine reptiles of its time, Plesiosaurus developed a specialized set of broad, flat teeth that served a very particular purpose: crushing hard-shelled prey. The most striking feature of Plesiosaurus was its dental adaptation. The front of its jaw contained chisel-like teeth for picking up food, while the roof of its mouth and lower jaw were equipped with large, flat plates, hence the name Plesiosaurus plates. These plates weren't actually teeth in the conventional sense, but rather modified dental structures that functioned like built-in mortars and pestles. Can you imagine having natural crushing plates in your mouth? These dental plates were crucial for Plesiosaurus' survival strategy. They were used to crush and grind shellfish, mollusks, and other hard-shelled creatures that lived on the seafloor. This adaptation allowed Plesiosaurus to access a food source that many other marine predators couldn't exploit. Think of it as the Triassic equivalent of a modern-day sea otter, which also specializes in crushing shellfish. But Plesiosaurus' adaptations didn't stop at its teeth. The creature's body was also specially modified for its lifestyle. Growing to about 2 meters (6.6 feet) in length, Plesiosaurus had a robust, heavily built body protected by thick, bony plates along its back. These plates served as armor, protecting it from predators while it foraged along the shallow coastal waters of the Triassic seas. The creature's body shape was also quite unique. Unlike the streamlined ichthyosaurs we discussed in the previous act, Plesiosaurus had a more barrel-shaped body. This shape was perfect for its bottom-dwelling lifestyle, allowing it to maintain stability while feeding on the seafloor. Its limbs were modified into paddle-like structures, but they weren't as specialized for swimming as those of other marine reptiles of the time. Fossil evidence has given us remarkable insights into Plesiosaurus' habitat and behavior. These animals lived in the shallow coastal waters of what is now Europe, particularly in areas that were once part of the Tethys Sea. The sediments where Plesiosaurus fossils are found indicate these creatures preferred warm, shallow marine environments, much like modern-day coral reefs. What's particularly interesting about Plesiosaurus is its role in the larger ecosystem of the Triassic period. It represents one of the earliest examples of marine reptiles developing specialized feeding adaptations. This adaptation to a specific dietary niche helped Plesiosaurus avoid direct competition with other marine predators of its time. The evolution of Plesiosaurus also tells us something important about how reptiles adapted to marine life. Unlike the fully aquatic ichthyosaurs, Plesiosaurus represents an intermediate stage in the transition from land to sea. Its body structure suggests it could still move on land, similar to modern seals, though it spent most of its time in the water. Scientists have been able to study Plesiosaurus through numerous well-preserved fossils, particularly from German localities. These fossils have preserved not just the bones, but also impressions of the armor plates and dental structures, giving us a detailed picture of how these animals looked and lived. The extinction of Plesiosaurus, like many other Triassic marine reptiles, remains a subject of scientific investigation. What we do know is that these fascinating creatures disappeared before the end of the Triassic period, possibly due to changes in their environment or competition from other marine animals that were evolving at the time. Understanding Plesiosaurus helps us appreciate the incredible diversity of life that existed in Earth's ancient oceans. It shows us how evolution can produce specialized adaptations to fill specific ecological niches, and how these adaptations can lead to success in the competitive world of marine ecosystems. What makes Plesiosaurus particularly relevant to modern science is how it demonstrates the principle of convergent evolution, where similar adaptations evolve independently in different species facing similar environmental challenges. The crushing plates of Plesiosaurus are remarkably similar in function to the specialized teeth of modern-day rays and certain fish species that also feed on hard-shelled prey. In conclusion, Plesiosaurus represents a fascinating chapter in the evolution of marine reptiles, showing us how specialized adaptations can allow species to thrive in specific ecological niches. Its unique combination of crushing plates and armored body makes it one of the most interesting creatures of the Triassic seas, providing valuable insights into the diversity of life in Earth's ancient oceans. Let's dive deep into one of the most fascinating creatures that swam the ancient Cretaceous seas, the Hesperornis. Had you ever wondered what would happen if you combined a penguin, a loon, and a toothed beak? Nature already conducted this experiment about 80 million years ago, giving us this remarkable bird. Hesperornis was a flightless diving bird that ruled the waters during the late Cretaceous period, specifically from about 83.5 to 78.5 million years ago. But don't let the term bird fool you into thinking this was just another waterfowl. This creature was unlike any bird alive today, and its story helps us understand a crucial chapter in avian evolution. First, let's address the most striking feature of Hesperornis, its size. While modern diving birds like penguins and loons are relatively modest in size, Hesperornis was a giant among its kind, reaching lengths of up to 6 feet, 1.8 meters. Imagine encountering a bird the size of a human adult, perfectly adapted for life in the water. This impressive size made it one of the largest known birds of the Cretaceous period. But what made Hesperornis truly unique was its combination of features, some familiar to us from modern birds, others surprisingly primitive. Unlike today's birds, Hesperornis had teeth. Yes, you read that correctly, actual teeth in its beak. These weren't just any teeth. They were sharp, backward-pointing teeth set in a groove in its beak, perfect for catching and holding slippery prey like fish. This feature reminds us that birds evolved from toothed ancestors, and Hesperornis represents a fascinating transitional form in avian evolution. The anatomy of Hesperornis tells us a remarkable story about its lifestyle. Its legs were positioned far back on its body, similar to modern loons and graves. This placement made it an excellent swimmer, but would have made walking on land extremely awkward and difficult. In fact, scientists believe Hesperornis might have been even more aquatically adapted than modern diving birds, possibly only coming ashore to lay eggs, much like sea turtles do today. What about its wings? Here's where the story gets even more interesting. Hesperornis had extremely reduced wings, so small they were practically useless. This tells us that this bird had completely abandoned flight in favor of a fully aquatic lifestyle. But why would a bird give up the ability to fly? The answer lies in specialization. Hesperornis had become so well adapted to diving and swimming that it no longer needed flight capabilities. The fossil record has given us remarkable insights into how Hesperornis moved through water. Its powerful legs ended in lobed toes, similar to those of modern grebes. These would have provided excellent propulsion underwater, allowing the bird to chase after fish and squid with remarkable agility. Its bones were dense, helping it to stay submerged, unlike the light, hollow bones of flying birds. But life wasn't always easy for Hesperornis. It shared its marine environment with formidable predators, including mosasaurs and large predatory fish. How did it survive in such dangerous waters? Its speed and maneuverability underwater, combined with its large size, would have helped it avoid becoming prey while successfully hunting its own food. The distribution of Hesperornis fossils tells us another fascinating story. These birds weren't confined to a small area. Their remains have been found across what was once the Western Interior Seaway, a vast body of water that divided North America into two landmasses during the late Cretaceous. Fossils have been discovered from what is now Kansas to the Canadian Arctic, suggesting these birds were highly successful and widespread. What led to the ultimate extinction of Hesperornis? Like many Cretaceous animals, it disappeared during the mass extinction event at the end of the period, about 66 million years ago. The same catastrophe that claimed the non-avian dinosaurs also marked the end for this remarkable diving bird. However, its legacy lives on in the diverse array of diving birds we see today, from penguins to loons, each adapted in their own way to life in and around water. The story of Hesperornis challenges our preconceptions about birds and evolution. It shows us that evolution doesn't always follow a straight line toward modern forms. Sometimes it experiments with combinations of features we might never expect, like a toothed, flightless diving bird the size of a human. It reminds us that the history of life on Earth is full of surprising twists and turns, and that many remarkable creatures have come and gone, leaving only their fossils to tell their stories. Understanding Hesperornis helps us appreciate the diversity of life that has existed on our planet and the various ways animals have adapted to their environments throughout Earth's history. It stands as a testament to the remarkable adaptability of life and the endless possibilities that evolution can produce.